Hello there, and welcome to Science for Sleep, where we take a calm look at the universe, follow the evidence at an unhurried pace, and give the mind something interesting to think about while the rest of you gets comfortable. Tonight, we are travelling far beyond the familiar planets of our own solar system to visit a small world with a very large temperature problem. Its name is KOI-55b, and according to the estimates used by astronomers, its surface may be hotter than the visible surface of the Sun. That sentence sounds as though it should contain a mistake. We're used to thinking of planets as the cooler objects and stars as the hot ones. Earth is warmed by the Sun. Mercury is scorched by the Sun. Even the hottest planets we normally discuss are heated because they sit too close to their stars or trap enormous amounts of energy beneath thick atmospheres. A planet being hotter than the Sun seems to reverse the proper order of things, like finding an ice cube that has somehow boiled the kettle. Yet KOI-55b belongs to a system where the usual rules of planetary comfort stopped applying a very long time ago. It orbits a compact, intensely hot star that has already passed through one of the most violent stages in stellar evolution. The planet, or perhaps the dense remains of a much larger planet, circles so close that a complete year lasts only a few hours. There is no mild morning there, no cool evening, and no distant season waiting to bring relief. The star fills a large part of the sky, pouring radiation onto a world that may be slowly losing what little material it has left. Before we move closer, I would love to know where you are listening from tonight. Are you in a quiet room with the lights turned low, on a sofa after a long day, or already in bed while the clock makes a slightly unreasonable claim about how late it has become? You might also tell me what the weather is doing where you are. Perhaps rain is tapping against a window. Perhaps the air is warm and still. Perhaps it is cold enough that the idea of a planet heated to thousands of degrees feels especially remote. Wherever you are, your surroundings are almost certainly more pleasant than KOI-55b. Even the least cooperative bedroom temperature begins to seem manageable when compared with a place where rock may melt, vaporize, and become part of a thin stream of escaping material. There are many uncomfortable destinations in the universe, but this one would make even a broken hotel air conditioner look like excellent hospitality. If you find these slow journeys through science relaxing, you can give the video a like and subscribe to the channel. It helps other curious listeners find this quiet corner, especially those who enjoy ending the day with distant stars, strange planets, and explanations that do not arrive shouting. You can also leave your location in the comments, because there is something reassuring about seeing how many people, separated by countries and time zones, can listen to the same story beneath the same night sky. Now settle into a position that asks as little of you as possible. Let your shoulders loosen. Allow the room to remain exactly as it is. There is nothing you need to calculate, memorize, or solve. The numbers will be here when we need them, and we will handle them gently. Our destination is more than 1,000 parsecs away, so there is no need to rush. Space has already done enough rushing on our behalf. The name KOI-55b is not especially inviting. It sounds less like a planet and more like a label attached to a drawer in a very organised laboratory. KOI stands for Kepler Object of Interest, a practical title given to targets identified in data from NASA's Kepler Space Telescope. Kepler was designed to watch the brightness of stars with extraordinary patience, looking for tiny repeated changes that might reveal planets passing in front of them. Most of the worlds it helped uncover announced themselves through a small dip in starlight. KOI-55b was different. The star at the centre of this system is also known by other names, including KIC-5807616 and Kepler-70. It lies in the direction of the constellation Cygnus, the Swan, though it is far too faint to pick out with the unaided eye. The light reaching us from that part of the sky has crossed an immense distance. By the time it enters a telescope, it carries information from a system that no human spacecraft could approach within any reasonable span of history. We know the planet only through that light. There are no close photographs, No probe has skimmed over its surface. No instrument has sampled its atmosphere, assuming it has anything we would comfortably call an atmosphere. Astronomers worked from small variations in the star's brightness, patterns so subtle that they had to be separated from the star's own pulsations. This is one reason the system remains unusual and somewhat controversial. The planetary interpretation is still listed by NASA, but later analysis has questioned whether all of the signals truly come from orbiting worlds. That uncertainty does not make the story less interesting, it makes it more honest. Astronomy often begins with a signal that could have more than one explanation. A distant star brightens, dims, shifts, or trembles. Researchers compare possibilities, test models, gather more observations, and sometimes revise what they thought they knew. The universe does not provide labels. We make the labels ourselves, usually after a great deal of work and at least one meeting that should have been an email. For our journey, we will treat KOI-55b as the proposed world described in the Discovery interpretation, while keeping the uncertainty nearby rather than hiding it. That gives us two connected mysteries. First, what kind of object could survive in such an extreme orbit? Second, how can astronomers decide whether the tiny signal really belongs to a planet at all? The proposed planet is smaller than Earth. Estimates place its radius at roughly 3/4 of Earth's radius and its mass at less than half of Earth's. Those values suggest a compact terrestrial object rather than a gas giant in its present condition. The phrase "in its present condition" matters, because KOI-55b may not have started small. Its host star is not a normal star like the Sun. It is a hot subdwarf, a stripped stellar core left after a red giant lost most of its outer layers. To understand why that matters, imagine the future of our own Sun, although we have no need to become personally concerned about the schedule. Billions of years from now, the Sun will exhaust the hydrogen in its centre and expand into a red giant. Its outer atmosphere will swell far beyond its current size. The inner planets will face a very bad period for property values. KOI-55 star has already been through something similar. At some point, it expanded dramatically. If a large planet once orbited nearby, the star's outer layers could have surrounded it. The planet would then have moved through hot stellar gas while gravity, drag, and intense heating stripped away its atmosphere and outer material. Instead of being completely destroyed, a dense core may have survived. That remaining core could be what we now call KOI-55b. This idea is remarkable because planets are usually introduced as objects that form around young stars. They gather from disks of gas and dust, settle into orbits, collide, migrate, and eventually become the systems we observe. KOI-55b may represent something very different. Not a newly formed planet, but the remainder of an older one after its star nearly consumed it. It could be a planetary survivor, though survivor sounds rather comfortable for an object still being roasted at close range. The orbit itself gives a clear sense of the problem. KOI-55b is thought to circle its star at only about 0.006 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun. This planet sits at a tiny fraction of that distance. Its orbital period is about 0.24 Earth days, which works out to less than 6 hours. In the time between going to bed and waking in the morning, KOI-55b could complete an entire trip around its star. A 6-hour year would make calendars wonderfully compact. Birthdays would become exhausting. Seasonal decorations would need a dedicated staff. Fortunately, there are probably no residents there trying to keep track. Being close to a star does more than shorten the year. It increases the amount of radiation reaching the planet and strengthens tidal forces. KOI-55b is likely tidally locked, meaning the same side may always face the star while the opposite side remains turned away. On many tidally locked planets, that arrangement creates a permanent day side and a permanent night side with winds carrying heat between them. On this world, the distinction may not offer much comfort. The night side could still be heated by molten material, conducted energy, or any remaining vapor surrounding the planet. NASA describes an estimated temperature of about 6,800 degrees Celsius, or roughly 12,000 degrees Fahrenheit. The visible surface of the Sun is around 5,500 degrees Celsius. That's the comparison behind the title, The Planet Hotter Than the Sun. It does not mean KOI-55b contains more energy than the Sun, nor does it mean every part of the Sun is cooler. The Sun's interior reaches millions of degrees. It means the planet's estimated temperature may exceed the temperature of the layer of the Sun that we normally see. The distinction is useful because dramatic descriptions can become misleading when the details are removed. KOI-55b is not a miniature star. It does not generate energy through sustained nuclear fusion. It is a small object exposed to extreme heating from an even hotter star. Its host has an effective temperature of roughly 27,700 Kelvin, far hotter at the surface than our Sun. The planet is therefore less like a glowing furnace that heats itself, and more like a piece of material held dangerously close to an industrial torch. What would matter look like there? At temperatures of several thousand degrees, familiar rocks would not remain as quiet, solid ground. Minerals can melt. Some can boil or break apart into their chemical components. Metals may exist as vapour. A thin atmosphere, if one persists at all, could be made from material released directly from the surface. Instead of water clouds, there might be clouds or streams involving vaporized rock and metal, though the exact conditions depend on composition, heat distribution, pressure, and whether the object is actively losing mass. We should be careful not to decorate the planet with details we have not measured. It is tempting to imagine bright lava oceans, glowing cliffs, and winds carrying iron vapour around the globe. Some of those conditions are physically plausible for ultra-hot rocky worlds, but KOI-55b has not been mapped. The safest picture is simpler. It is likely an extremely heated, compact object, close enough to its star that solid surface material would struggle to remain solid across much of the illuminated side. There is another reason to move carefully. The planet may be evaporating, but astronomers do not have a camera showing a visible tail streaming behind it. The claim comes from models of how such a small object might respond to enormous stellar radiation. In astronomy, words such as may, could, and likely are not signs that scientists are being evasive. They are tools for separating observation from interpretation. A good explanation leaves those tools in place. That may sound less dramatic than declaring that we have found a world made entirely of liquid metal, but reality rarely suffers from a shortage of drama. A proposed sub-Earth-sized remnant circling the exposed core of a star every few hours is strange enough without adding furniture. As you listen, consider the ordinary relationship you have with sunlight. You might notice it warming one side of a room. You might close a curtain when the glare reaches a screen. You may step outside on a cold morning and stand in a bright patch because it feels a little better there. The energy crossing space from our Sun supports weather, plants, oceans, and nearly every familiar ecosystem on Earth. We live at a distance where sunlight can warm without immediately taking the planet apart. KOI-55b occupies the opposite kind of arrangement. Its star is not a gentle point in the sky. From the planet's orbit, the star would appear enormous compared with the Sun as seen from Earth. There would be no blue sky in the earthly sense, and possibly no stable sky at all. The light would be harsh and rich in high-energy ultraviolet radiation. Any surface facing the star would be exposed continuously if the world is tidally locked. The planet's short orbit also means it moves quickly. Gravity pulls it inward, while its sideways motion carries it around the star. This balance repeats every few hours, producing a system that is compact, fast, and difficult to imagine at human scale. We are used to seeing planets as slow wanderers. Mars takes nearly 2 Earth years to circle the Sun. Saturn takes more than 29. KOI-55b could finish several orbits during one long film, though choosing a film that lasts that long may present a separate challenge. Its closeness raises questions about stability. Why has it not fallen into the star? How did it reach that orbit? Did it move inward while the star expanded? Was it dragged through the red giant envelope? Could interactions with another planet have helped place it there? The proposed companion, KOI-55c, circles slightly farther out, completing an orbit in a little over 8 hours. Together, the signals were interpreted as evidence for a compact pair of small bodies around the hot subdwarf. A system like this forces us to rethink what the word planet can include. The first exoplanets discovered around ordinary stars encouraged comparisons with Jupiter, Neptune, and Earth. Later surveys revealed hot Jupiters, super-Earths, mini-Neptunes, lava worlds, and planets in resonant chains. KOI-55b, if confirmed as described, extends the category toward planetary remnants, objects shaped not only by formation but by survival after stellar catastrophe. There is a useful lesson hidden in that variety. Nature does not build planetary systems from a single standard plan. Stars differ in mass, age, temperature, and chemical history. Planets form at different distances and migrate through changing disks. Large worlds scatter small ones. Orbits stretch, tilt, and sometimes collapse. Then the stars themselves evolve, altering the environment again. A planet that seems impossible around a young sun-like star might become possible around the exposed core of an old giant, though possible does not mean pleasant. Our own solar system feels orderly because we have learned its pattern. 4 small planets sit close to the Sun. 4 giant planets orbit farther out. Smaller bodies fill the gaps and edges, yet even here, the arrangement is the result of ancient movement and collision. Elsewhere, we find systems that compress several planets inside the orbit of Mercury, giant worlds skimming their stars and bodies moving around stellar remnants. KO-55 belongs to that broader collection of reminders that the universe was not designed with textbook diagrams in mind. It is also a reminder that a star's death is not a single event. Stellar evolution unfolds in stages. A star can expand, shed matter, expose a hot core, cool, and change again over very long periods. Planets around it may be swallowed, stripped, shifted, shattered, or ejected. Some might survive far away with altered climates. Others could pass through the expanded envelope and emerge as dense remnants. Each outcome depends on mass, distance, composition, and timing. The host of KOI-55b is especially important because it is a pulsating hot subdwarf. Its brightness changes in regular ways as waves move through the star. Those pulsations allow astronomers to study its interior through a method called astroseismology. Just as earthquakes reveal layers inside Earth, stellar oscillations reveal information about conditions inside a star. Kepler recorded those tiny changes with remarkable precision. Hidden among the stellar pulsations were additional periodic signals. They repeated at intervals matching the proposed orbital periods of KOI-55b and KOI-55c. Researchers interpreted them as changes in brightness caused by the intensely heated sides of the planets, moving in and out of view. A hot day side would contribute a tiny amount of extra light when facing us, and less when turned away. The signal was not the usual shadow of a planet crossing a star. It was closer to detecting the changing glow of the object itself. Imagine trying to notice a warm grain of sand beside a searchlight, then trying to decide whether its faint flicker is real or part of the searchlight's own vibration. That is not a perfect comparison, but it gives a sense of the difficulty. The star dominates the observation. The proposed planets contribute only subtle patterns. Extracting those patterns requires long data sets, careful frequency analysis, and a willingness to question the result when new methods become available. Later researchers did question it. Alternative analyses suggested that some of the low-frequency signals might come from the star or from instrumental effects rather than planets. NASA's Exoplanet Archive continues to list KOI-55b as a confirmed planet, while also flagging it as controversial. That mixed status is worth remembering throughout our journey. We are not visiting a world whose every feature has been firmly measured. We are examining a compelling interpretation of a difficult signal around a very unusual star. Science can hold both ideas at once. KOI-55b can be one of the most fascinating proposed planetary remnants ever reported, and its existence can still deserve further scrutiny. Curiosity does not require certainty. In fact, uncertainty often gives curiosity somewhere useful to go. For now, picture only the scale of the system. A compact blue-white star, much smaller than the Sun but far hotter at its visible surface, occupies the centre. Very close to it, a small body races around in under 6 hours. Its star-facing side absorbs an extreme flood of radiation. The material at its surface may be molten, vaporized, or escaping. A second proposed world moves nearby on an orbit lasting a little over 8 hours. Far away, Kepler watches their combined light as a row of numbers. Moving closer to KOI-55b does not immediately make it easier to see. The planet is far too small, too distant, and too close to its star for any telescope to photograph as a separate world. There is no clear image showing a round surface beside a glowing sun. What astronomers have instead is a collection of measurements, repeating signals, and carefully tested estimates. From those pieces they have constructed the best available description of an object, unlike anything in our own solar system. KOI-55b is located roughly 4,000 light-years from Earth, in the direction of the constellation Cygnus. That distance means the light recorded by the Kepler telescope began its journey thousands of years before modern astronomy existed. By the time those photons reached our instruments, human beings had built cities, changed languages, crossed oceans, invented clocks, argued about clocks, and eventually launched a spacecraft capable of detecting tiny variations in the brightness of a distant star. The planet is also known as Kepler 70b. Astronomical objects often collect several names because different surveys, catalogues, and research teams identify them in different ways. KOI-55 refers to the Kepler object of interest connected with the star. Kepler 70 is another designation for the system. The lowercase letter b tells us that this was the first proposed planet associated with the star. The lettering can seem slightly odd at first. The star itself is normally treated as component A, whether or not anyone says the letter aloud. The first planet becomes B, the next becomes C, followed by D, E, and so on. There is no planet A waiting nearby and feeling overlooked. Astronomy has simply decided that the star gets first place in the alphabet, which seems reasonable considering it contains almost all the mass and is doing most of the glowing. According to the original interpretation, KOI-55b has a radius about 76% that of Earth. If the estimate is correct, its diameter would be close to 9,700 kilometers. That makes it smaller than Earth, but larger than Mars. It would not look like a tiny asteroid or an irregular chunk of debris. Gravity would probably have pulled it into a roughly spherical shape, assuming it has remained intact under the intense forces acting upon it. Its estimated mass is around 44% of Earth's mass. These figures suggest an object with an average density broadly comparable to that of a rocky planet, although the numbers are not as direct or secure as measurements made for a nearby transiting world. The proposed mass and radius depend on models of the light signal, the system's inclination, the planet's reflectivity, and the amount of heat it releases. That distinction is important. Astronomers did not watch KOI-55b pass clearly across the face of its star and measure a neat shadow. They did not detect the star moving back and forth through a strong radial velocity signal caused by the planet's gravity. The object was inferred from small periodic changes in brightness that appeared after the stronger pulsations of the star had been analysed. The result is a planet that can be described numerically, but not inspected directly. We can estimate its size, we can calculate its orbit, we can model its temperature, we can discuss what materials might remain on it. Yet we cannot point to a photograph and say, there is the surface, and that bright patch is a particularly unpleasant place to stand. If KOI-55b is close to the published mass and radius, its surface gravity may be roughly 3/4 of Earth's. On an ordinary cool planet, that might make movement feel slightly easier. A person who weighed 80 kilograms on Earth would still have the same mass, but the downward pull would feel weaker. That observation is of limited practical value here. Lower gravity would not help with the temperature, radiation, lack of breathable air, or immediate destruction of almost any equipment we currently know how to build. You might be able to jump higher, but only very briefly, and without the opportunity to mention it afterward. The most striking feature of KOI-55b is its orbit. The planet is thought to travel around its star at a distance of only 0.006 astronomical units. 1 astronomical unit is the average distance between Earth and the Sun, almost 150 million kilometers. Multiplying that by 0.006 gives an orbital distance of about 900,000 kilometers from the center of the star. That may sound large because 900,000 kilometers is far beyond anything we normally travel. It is more than twice the average distance between Earth and the Moon. Within the scale of a planetary system, however, it is extremely close. Mercury, the innermost planet in our solar system, orbits the Sun at an average distance of about 58 million kilometers. KOI-55b is more than 60 times closer to its star than Mercury is to ours. The host star is much smaller in radius than the Sun, so the planet is not physically moving through its present visible surface. Even so, the gap is narrow by astronomical standards. The star would dominate the sky. Using the published estimates for the stellar radius and orbital distance, it could appear roughly 18 degrees wide as seen from the planet. For comparison, the Sun seen from Earth is about half a degree across. You can cover it with the tip of a finger held at arm's length, though looking directly at it is not advisable. From KOI-55b, the host star could appear more than 30 times wider. It would take up an area of sky well over 1,000 times larger than the Sun does from Earth. There would be no need to wonder whether morning had arrived. The star would make its presence reasonably clear. The planet completes one orbit in about 5.76 hours. A year on KOI-55b therefore lasts less than 6 Earth hours. By the time someone on Earth has eaten breakfast, worked through the morning, and begun thinking about lunch, the planet may have completed an entire year and started another. During one Earth day, KOI-55b circles its star a little more than 4 times. During one Earth year, it completes roughly 1,500 orbits. Celebrating every local New Year would be impractical. By the time the decorations were put away, another celebration would already be overdue. This short period also tells us the planet is moving extremely quickly. Based on its estimated orbital distance and period, its speed would be around 270 kilometers per second. Earth moves around the Sun at approximately 30 kilometers per second. KOI-55b may therefore travel around its star about 9 times faster than Earth travels around ours. Nothing on the planet would feel that speed in the simple sense of wind rushing past. The world, its surface, and anything attached to it would all be moving together. We do not feel Earth racing around the Sun because constant motion through space does not produce a sensation on its own. Changes in motion are what we notice. The orbit would still shape nearly every aspect of the planet's condition. At such a small distance, the gravitational pull of the star is enormous. The planet must move rapidly to avoid falling inward. Its orbital path is a continuous balance between that inward pull and its forward movement. The same gravity would create strong tides. On Earth, the Moon raises tides in the oceans and slightly deforms the solid ground beneath our feet. KOI-55b experiences tidal forces from a star much more massive than any moon and located remarkably close by. Over time, those forces would be expected to affect the planet's rotation. It is likely, although not directly observed, that KOI-55b is tidally locked. That would mean it rotates once during every orbit, keeping one side turned toward the star and the other facing away. Our moon is tidally locked to Earth, which is why we always see almost the same lunar hemisphere. The moon still rotates, but it completes one turn in the same amount of time it takes to orbit Earth. KOI-55b may perform the same arrangement at much greater speed, completing both its rotation and orbit in under 6 hours. If it is tidally locked, there would be a permanent day side, a permanent night side, and a narrow region between them where the star remains near the horizon. On a more moderate planet, scientists might discuss whether winds or oceans could transfer heat from one hemisphere to the other. Here, the temperature is so extreme that even the night side may be a deeply hostile environment. The day side receives a continuous flood of light and high-energy radiation. There is no sunset to interrupt the heating. Any atmosphere capable of circulating around the planet would carry some energy toward the night side, but whether a substantial atmosphere can survive is uncertain. Material may be constantly stripped away by radiation and the planet's relatively weak gravity. NASA gives a temperature estimate of about 6,800 degrees Celsius, or roughly 12,000 degrees Fahrenheit. The number should not be mistaken for a precise thermometer reading taken from the surface. It is a calculated estimate based on the energy received from the star and assumptions about how that energy is absorbed and redistributed. Even with that caution, it is an extraordinary value. The visible surface of our Sun, known as the photosphere, has a temperature of about 5,500 degrees Celsius. KOI-55b may therefore be more than 1,000 degrees hotter than the part of the Sun we normally see. The comparison needs one important qualification. The interior of the Sun is much hotter. Its core reaches around 15 million degrees Celsius, where nuclear fusion releases the energy that eventually escapes into space. KOI-55b is not hotter than the entire Sun, and it is not producing energy through fusion like a star. It is hotter than the Sun's visible outer surface according to the published estimate. That is still unusual enough. A planet does not need to defeat a star in every possible category to make its point. The host star itself is far hotter at the surface than our Sun. Its effective temperature is estimated at approximately 27,700 Kelvin, equivalent to about 27,400 degrees Celsius. KOI-55b is therefore orbiting a compact star whose surface is several times hotter than the planet. The title, "The Planet Hotter Than the Sun," works because most people understand the Sun to mean the bright surface we see from Earth. It does not mean the planet is hotter than its own star. If it were, the system would require an entirely different explanation, and probably a much longer health and safety form. At 6,800 degrees Celsius, the usual image of a rocky surface becomes difficult to maintain. Earth's crust contains minerals built from compounds involving silicon, oxygen, aluminium, iron, magnesium, calcium, and other elements. Many of those substances melt at temperatures well below the estimate for KOI-55b. Raise the temperature further, and they begin to vaporize or break apart. A surface exposed to the star could consist partly of molten material, but at the highest temperatures, even a global ocean of lava may be too simple a description. Rock itself could enter the atmosphere as vapor. The gas above the surface might contain atoms and ions of sodium, iron, silicon, magnesium, oxygen, and other products released from heated minerals. This does not mean astronomers have detected iron clouds or mapped rivers of lava on KOI-55b. Those are possible outcomes based on physics and comparisons with models of very hot rocky exoplanets. The exact composition of this world is unknown. We do not know what the original planet was made from, how much was removed, or what layers now form the visible exterior. If KOI-55b began as a gas giant, its present surface may once have been buried beneath tens of thousands of kilometers of hydrogen and helium. A planet similar to Jupiter does not have a simple solid boundary where an astronaut might land. Pressure rises gradually through deep layers of gas and fluid, eventually reaching dense material nearer the centre. During the red giant phase of the host star, those outer layers may have been stripped away. The surviving object could be the core of the former giant, containing compressed rock, metal, and heavier compounds. It might be more accurate to think of it as the exposed interior of a planet, rather than a small rocky planet that always resembled its current form. Astronomers sometimes use the term Chthonian planet for a world that began as a gas giant and lost its gaseous envelope, leaving behind a dense core. The word comes from an ancient Greek term associated with the underworld. It is an appropriate name for an object that may have passed through the atmosphere of a red giant and emerged smaller, hotter, and generally less suitable for tourism. Whether KOI-55b truly followed that path is still uncertain. It may have started as a giant planet, a smaller gas-rich world, or something else entirely. The original researchers proposed that one or more large planets could have entered the expanding star's envelope, lost mass, and helped remove the star's own outer material. In that model, the planets were not merely passive victims. Their motion through the stellar envelope transferred energy and angular momentum into the surrounding gas. This interaction may have helped the star eject its outer layers, leaving the hot subdwarf we see today. It is an unusual possibility. The star may have transformed the planet, while the planet may also have influenced the star's transformation. Neither object left the encounter unchanged. At its current distance, KOI-55b is exposed not only to visible light and heat, but also to ultraviolet radiation. Hot subdwarf stars emit a substantial amount of high-energy light. Ultraviolet photons can heat gases, break molecules apart, remove electrons from atoms, and drive atmospheric escape. If material is vaporized from the planet's surface, radiation can push and heat that gas further. Some of it may escape the planet's gravity entirely. Over time, the world could continue losing mass, becoming smaller as its surface is gradually removed. Descriptions sometimes say the planet is evaporating. That is a useful general phrase, but it should not be imagined as a small puddle, quietly disappearing on a warm afternoon. The process may involve melting, vaporization, ionization, stellar radiation, and the escape of atoms into space. It is evaporation conducted with the universe's least subtle heating equipment. How quickly the planet could lose material depends on many unknowns. Its composition matters, its true mass matters, the intensity and spectrum of the star's radiation matter. Magnetic fields may matter. The efficiency with which absorbed energy drives material away also matters. Because of those uncertainties, it is difficult to give the planet a reliable remaining lifetime. It may be changing slowly compared with a human life, but rapidly compared with the lifetime of a planetary system. Astronomy often uses the phrase short-lived for events that continue for millions of years, which is one reason astronomers are rarely troubled by long queues. The planet may also be close enough for the star's gravity to affect its shape. A perfectly isolated planet would settle into something close to a sphere. Strong tidal forces can stretch a nearby object slightly along the line pointing toward its star. KOI-55b could therefore be somewhat elongated rather than perfectly round. If it moved too close, it would approach a boundary known as the Roche limit. Inside that region, tidal forces can overcome the gravity holding an object together, causing it to break apart. The exact location of the Roche limit depends on the density and internal strength of both bodies. KOI-55b appears to remain outside the present star, and models allow it to maintain an orbit, but its environment is not gentle. It circles near a gravitational boundary where distance makes an enormous difference. A small inward shift could increase the heating and tidal stress considerably. Its companion, KOI-55c, is proposed to orbit slightly farther out. KOI-55c has an estimated radius around 87% of Earth's, and a mass around 66% of Earth's. Its orbit lasts about 8.23 hours at a distance of roughly 0.0076 astronomical units. The two proposed planets are separated by a modest distance and move around the star in a compact arrangement. Their orbital periods are close to a ratio that may have been shaped by past gravitational interaction, although the exact dynamical history is difficult to reconstruct. If both objects are real, they may be fragments or surviving cores produced during the same period of stellar evolution. Perhaps two giant planets entered the red giant's envelope. Perhaps one larger object broke into multiple pieces. Perhaps the system experienced migration and disruption, more complicated than either simple picture. Each scenario comes with problems. Two planets surviving engulfment would require both to lose enormous amounts of material without being destroyed. A broken core would need to produce fragments that settled into stable, closely spaced orbits. Researchers compare these possibilities because no ordinary formation model places small, rocky worlds so close to a star that later expanded far beyond their orbits. There is another complication. The signals assigned to KOI-55b and KOI-55c may not come from planets at all. The host star pulsates at many frequencies. When a star produces several oscillations at once, combinations of those frequencies can sometimes create additional patterns in the data. A later analysis argued that the two supposed orbital frequencies could be related to combinations of stellar pulsations. Under that explanation, astronomers may have mistaken part of the star's own behaviour for the glow of orbiting planets. NASA's Exoplanet Archive continues to list KOI-55b and KOI-55c as confirmed planets, but it also marks both as controversial. That status is not common, but it reflects the way scientific catalogues preserve published results while noting serious later questions. For a listener, it may feel frustrating to spend time meeting a planet and then hear that the planet might not be there. Astronomers experience a similar frustration, though they usually express it with graphs. The uncertainty is not a reason to abandon the object. It is part of what makes the system valuable. KOI-55b teaches us about the difficulty of detecting small bodies around active or pulsating stars. It encourages researchers to improve methods for separating planetary signals from stellar variation. If the planet is real, it provides evidence that planetary cores can survive extreme stellar evolution. If it is not, the mistaken identification still reveals something important about how complex stars can imitate planets. For the moment, we can hold the proposed world in a sensible middle position. We do not need to treat every estimate as certain, and we do not need to dismiss it completely. We can say that Kepler detected a repeating signal, that a respected research team interpreted the signal as a small, intensely heated planet, and that later work offered another explanation. That is often how the edge of knowledge looks. The clear facts occupy the centre. The uncertain interpretations gather around them. New observations slowly move the boundary. Suppose the planetary interpretation is correct. What would an observer see while approaching KOI-55b from a safe distance? The host star would appear as a brilliant blue-white disk. Its light would overwhelm the faint glow of the planet. Specialized instruments might detect the planet's heated hemisphere as a small addition to the system's total brightness. The planet itself might glow visibly because of its temperature. Objects heated to thousands of degrees emit substantial thermal radiation. Hot metal in a furnace changes from dull red to orange, yellow, and eventually white as its temperature rises. KOI-55b could radiate strongly across visible and infrared wavelengths, although the far brighter star would remain difficult to separate from it. Its day side may be covered by a surface that is liquid, gaseous, or continually changing between states. Dense material could circulate beneath the most exposed layers. Vapor might rise, move toward cooler regions, condense, and then return toward the day side. On some lava planet models, rock vapor can form an atmosphere that flows away from the hottest point. Minerals may condense on the cooler hemisphere and fall back toward the surface. KOI-55b might experience a version of that process, though the exceptional temperature could keep more material in gaseous or ionized form. the night side would not necessarily be dark in the familiar sense. Molten material can glow. Heat transported through the interior or atmosphere could keep much of the surface luminous. The nearby star might also illuminate particles escaping around the planet. There would be no ordinary weather, no water cycle would survive. Molecules that are stable in Earth's atmosphere would be broken apart. The movement of vaporized minerals and charged particles would be driven by differences in temperature, pressure, radiation, and magnetic forces. The word surface itself may become inconvenient. On Earth, the boundary between ground and atmosphere is obvious. On a world where the ground is boiling into gas, the transition may be less tidy. There could be a dense lower layer of mineral vapor above molten material, thinning gradually with altitude before escaping into space. Even the idea of day and night might be complicated by heat circulation and the size of the star in the sky. At the boundary between the hemispheres, the star would not appear as a small object slipping neatly below the horizon. Its wide disk would take time to set across the curved landscape. Some regions could see part of the star while the rest remained hidden. None of this would be stable on human timescales in the way a quiet landscape seems stable. The planet races through its orbit. The star pulsates. Radiation strikes the surface. Material heats, moves, and escapes. Tidal forces pull continuously through the interior. Still, the orbit itself may have continued for millions of years. A system can be violently active in local conditions while remaining mathematically stable over long periods. KOI-55b does not need to be comfortable to be persistent. That persistence is the central mystery. A small planet could not have formed in its present orbit around the star as we see it today without facing serious difficulties. The star is an evolved object. It has already expanded beyond its former size, lost most of its outer envelope, and contracted into a hot compact state. Any planet now sitting at 0.006 astronomical units must have a history connected with that transformation. Either it moved inward, survived being surrounded by stellar gas, formed from material after the envelope was lost, or has been incorrectly identified. The first possibility is the one that made KOI-55b famous. A larger planet entered the expanded star, spiraled inward, lost nearly everything, and emerged as a bare core. It is an explanation that turns the current world into evidence of an earlier disaster. The star responsible for KOI-55b's extreme conditions is usually called KOI-55, KIC 5807616, or Kepler 70. None of those names tells us much about what it actually is. Seen through an ordinary telescope, it would look like a faint point of light in the direction of Cygnus. Measured more carefully, it becomes clear that this is not an ordinary point of light at all. It is the exposed core of a star that has already completed the large, familiar part of its life. Calling it a star that died once is useful, but it needs a small correction. KOI-55 is not dead in the strict astronomical sense. It is still producing energy through nuclear reactions. It has not become a cold, dark object, and it has not yet settled into its final state as a white dwarf. What ended was its earlier life as a normal star with a broad hydrogen-rich exterior. That version of the star is gone. The object now shining at the centre of the system is a hot subdwarf B star. Astronomers shorten that to SDB star, which is easier to say and leaves more time for staring at graphs. A hot subdwarf is smaller and less massive than the Sun, but its exposed surface is much hotter. It represents a temporary stage between the red giant phase and the white dwarf stage. KOI-55 has a mass close to half the mass of the Sun. Estimates based on spectroscopy and its pulsations place it at about 0.496 solar masses. Despite containing so much material, its radius is only around 1/5 of the Sun's radius. That gives it a very high density and a powerful surface gravity. The Sun has an effective surface temperature of about 5,800 Kelvin. KOI-55 has an effective temperature of roughly 27,700 Kelvin. Its surface is therefore almost 5 times hotter in temperature than the Sun's visible surface. It emits a large share of its energy in ultraviolet light, which human eyes cannot see but nearby matter would certainly notice. Its colour would be blue-white rather than the warmer white-yellow appearance associated with the Sun. From a safe distance it might look small and intensely bright. From the orbit of KOI-55b, it would occupy an enormous part of the sky and produce a continuous flood of radiation. The star did not begin this way. Long before it became a compact blue object, it would have spent most of its existence on the main sequence, the long stable period when a star produces energy by fusing hydrogen into helium in its centre. Our Sun is currently in that stage. During the main sequence, gravity pulls a star inward, while heat and pressure from nuclear fusion push outward. When those effects remain balanced, the star can stay relatively stable for billions of years. It changes slowly, but not in ways that are obvious during a human lifetime. Hydrogen fusion gradually builds a growing amount of helium in the core. Helium is heavier than hydrogen and requires higher temperatures before it can begin fusing efficiently. Once the central hydrogen supply becomes depleted, the balance inside the star changes. Fusion does not stop everywhere at once. Hydrogen can continue burning in a shell around the helium-rich centre. The core contracts under gravity, which increases its temperature. The outer layers respond by expanding. This is how a star leaves the main sequence and becomes a red giant. Its radius increases greatly, while its outer surface becomes cooler. The name red giant refers to that cooler surface colour and enormous size, not to a reduction in the total amount of energy being released. Our Sun will eventually undergo the same general transformation. It will expand until its outer layers reach far beyond their present location. Mercury and Venus are expected to be engulfed. Earth's precise fate depends on the competing effects of the Sun's expansion, mass loss, and the changing orbit of our planet. But conditions here will become uninhabitable long before the final result requires discussion. KOI-55 has already passed through its own version of this process. Its former outer atmosphere expanded across a huge region of space. Any planets orbiting close to the star would have found themselves inside it. That phrase can sound confusing. We normally picture the surface of a star as a clear boundary. A solid object has an edge, and a person can usually tell whether they are inside it or outside it. A red giant does not have a firm surface. Its atmosphere becomes thinner gradually with distance. A planet entering that atmosphere would first encounter very thin gas. As the star expanded farther, the density around the planet would increase. The planet could continue orbiting while surrounded by stellar material, much as a satellite circles Earth while moving through the extremely thin upper atmosphere, except the conditions inside a red giant are far more destructive. The gas would create drag. The planet would lose orbital energy and begin spiraling inward. Friction and shocks would heat the surrounding material. The planet's motion could also transfer energy and angular momentum into the star's envelope. This stage is known as common envelope evolution, when a companion object and a stellar core become enclosed within the same expanded atmosphere. It is usually discussed in relation to two stars, but a sufficiently massive planet or brown dwarf could, in principle, take part in a similar interaction. Common envelope evolution is one of the most difficult processes in stellar astrophysics to model. The event may develop over a short period by astronomical standards. Gas moves in 3 dimensions: gravity, turbulence, radiation, shocks, rotation, and changes in the companion's orbit all influence one another. Researchers understand the broad idea better than the fine details. The companion falls inward and releases orbital energy. Some of that energy can help push the envelope away from the central star. If enough material is expelled before the companion is destroyed or reaches the core, a compact system may remain. In the case of KOI-55, most of the original hydrogen-rich envelope disappeared. The star was left with a helium-rich core covered by only a very thin layer of hydrogen. With the thick outer atmosphere removed, the much hotter interior became visible. This is why KOI-55 is both smaller and hotter than the Sun. A red giant is enormous because its outer layers are spread across a large volume. Strip those layers away and the remaining core contracts into a compact body. The temperature seen at its surface rises because we are no longer looking at the cool outer atmosphere that once surrounded it. Size and temperature do not always increase together. A large red giant can have a relatively cool surface, while a compact subdwarf can have a very hot one. Stars are inconsiderate enough to use several properties at once. The present star is not simply a cooling ember. Its mass was high enough, and its interior became hot and dense enough to ignite helium fusion. In the core, helium nuclei combine through reactions that produce carbon and oxygen. This helium burning stage places KOI-55 on what astronomers call the extreme horizontal branch. The name comes from the positions of such stars on a Hertzsprung-Russell diagram, a chart that compares stellar luminosity and temperature. For someone listening in bed, the important point is that KOI-55 is living through a stable but temporary period after losing almost its entire envelope. A normal red giant retains a large hydrogen-rich exterior, while helium burning begins in the centre. A hot subdwarf has nearly the same kind of helium-burning core, but very little envelope around it. Without a thick outer layer, it cannot return to the broad red giant form in the usual way. Eventually, the helium in the core will also become depleted. The star will then move through later stages, shed or rearrange what little surrounding material remains, and head toward the white dwarf sequence. As a white dwarf, it will no longer maintain sustained fusion. It will cool slowly over an extremely long period. The present hot subdwarf stage is therefore positioned between two very different appearances. Earlier, the star was a large red giant. Later, it will become a compact white dwarf. At the moment, it is small, blue-white, extremely hot, and still powered by helium fusion. This is why saying that it has died once is not entirely wrong. Its first stable identity ended. It exhausted the central fuel that supported its main sequence life, expanded into a giant, lost almost all of its outer material, and emerged as something that would look completely unfamiliar beside its former self. Imagine replacing the Sun with an object half as massive, 1/5 as wide and almost 5 times hotter at the surface. Earth would not remain as it is. Even at our current distance, the change in radiation would be severe. KOI-55b is not 1 astronomical unit away. It is about 0.006 astronomical units from the star. The host's current radius is only a fraction of the planet's orbital distance, so KOI-55b moves outside the visible stellar surface today. During the red giant phase, however, the star's atmosphere would have extended far beyond the planet's present orbit. This creates the central problem. A planet could not simply remain untouched while the star swelled around it. If KOI-55b is real and existed before the red giant event, it must have undergone an extreme interaction. The world seen today may bear little resemblance to the original planet. A Jupiter-like object consists mostly of hydrogen and helium, with heavier material deeper inside. Those light outer layers would be especially vulnerable when surrounded by hot stellar gas. Heating would cause the atmosphere to expand. Drag would remove orbital energy. Tidal forces could distort the planet. Material could be stripped away and mixed into the star's envelope. As the orbit shrank, all of those effects would become stronger. A planet entering this environment would face 2 possible broad outcomes. It might be destroyed completely, its material becoming part of the star. Alternatively, a dense central region might survive after losing nearly everything around it. The original interpretation of the KOI-55 system favoured the second outcome. KOI-55b and its proposed companion may be the remaining cores of a larger planet that entered the red giant's envelope. Their inward motion may even have contributed to the removal of that envelope. The idea gives the planets an active role in the star's history. Their host damaged them, but their presence may have helped transform the host into a hot subdwarf. The energy released as they spiraled inward could have assisted in pushing stellar gas into space. There is a limit to how confidently this can be stated. Common envelope physics is uncertain, the planets themselves remain controversial, and no one observed the system during its red giant phase. Astronomers are reconstructing events from the properties visible now. The measured mass of the star is useful in that reconstruction. At about half a solar mass, it is close to the common mass expected for a helium-burning hot subdwarf. That supports the picture of a red giant core whose envelope was removed near the point when helium ignition became possible. Remove the envelope too early before the core has gained enough mass and temperature, and helium fusion may never begin. The exposed core would instead cool as a helium white dwarf. Remove it later, under suitable conditions, and the core can ignite helium and become an SDB star. KOI-55 appears to have landed in that narrow evolutionary category. Most of its mass is concentrated in the helium-burning interior. Only a very small amount of hydrogen remains near the surface. The star's high gravity causes different chemical elements in its atmosphere to behave in unusual ways. Heavier material tends to sink under gravity, while radiation can push certain ions upward. These processes, called gravitational settling and radiative levitation, affect the composition measured at the surface. This means the visible atmosphere does not provide a simple sample of the entire star. Some elements can appear unusually scarce, while others become concentrated in thin layers. Astronomers must account for those effects when interpreting the spectrum. A spectrum is produced by separating starlight into its component wavelengths. Atoms and ions absorb or emit light at particular wavelengths, leaving patterns that reveal temperature, chemical composition, pressure, and motion. For KOI-55, spectroscopy helped establish the effective temperature near 27,700 Kelvin and the high surface gravity expected from a compact star. Those measurements identified it as a hot subdwarf before the proposed planetary signals became the main attraction. The star also reveals itself through pulsations. It expands and contracts in small, complicated patterns. Different regions move at different times, creating variations in brightness that Kepler was able to measure. These are not explosions or dramatic changes in the entire star. The motions are more like vibrations travelling through a large sphere of gas. Some modes involve pressure acting as the main restoring force. Others are controlled largely by buoyancy within the star. Pressure modes, usually called P modes, tend to have shorter periods and probe the outer regions more strongly. Gravity modes, called G modes, have longer periods and can provide information about deeper layers. KOI-55 shows both kinds, making it a hybrid pulsator. Its light contains many overlapping frequencies produced by those oscillations. The brightness changes may be tiny, but they repeat with enough regularity for researchers to separate and analyze them. Studying stellar vibrations is known as astrosismology. The principle is similar to learning about Earth's interior from seismic waves produced by earthquakes. No one can travel into Earth's core, but waves moving through the planet respond to changes in density and composition. By measuring them at the surface, researchers can infer what lies below. Astroseismologists do something similar with stars. Each pulsation mode is influenced by the structure through which it travels. A collection of measured frequencies can constrain the star's mass, internal layering, rotation, and evolutionary state. Kepler was especially useful for this work because it monitored stars continuously for long periods. Ground-based telescopes must contend with daylight, weather, and the inconvenient rotation of Earth. A spacecraft can remain focused for much longer, producing a nearly uninterrupted record. The original goal of many KOI-55 observations was to study the star's pulsations, not to look for planets. The proposed worlds emerged from the low-frequency region of the brightness data after known stellar oscillations had been considered. That origin explains both the excitement and the later doubt. The star's vibrations made the detection possible because Kepler gathered such precise data for astrosismology. The same vibrations also created a complicated background capable of producing misleading signals. A star with many oscillation frequencies can generate patterns related to sums and differences between those frequencies. If two pulsations interact in the data, a weaker signal may appear at a frequency that resembles an orbital cycle. Later researchers argued that the signals attributed to KOI-55b and KOI-55c might be combinations of lower amplitude stellar pulsations. Under that interpretation, the supposed planets are products of the star's own changing brightness rather than separate bodies. The host star therefore occupies two roles in this story. Its past may explain how the planets were stripped into small remnants. Its present pulsations may explain why astronomers thought they had found the planets in the first place. Near the possibility is ordinary. Even without KOI-55b, the star is a valuable object. It offers a view of a red giant's exposed core while helium fusion is still continuing. Its pulsations allow researchers to examine internal layers that would otherwise remain hidden. With the planet included, the system becomes a test of whether planetary bodies can survive one of the most damaging stages of stellar evolution. The answer affects more than this distant system. It helps astronomers understand what can happen to planets around countless stars, including the eventual fate of worlds in our own neighbourhood. The Sun will not become a hot subdwarf in exactly the same way, without an interaction capable of removing its envelope at the right moment. It is expected to pass from the red giant phase toward a white dwarf through a different route. KOI-55 therefore should not be treated as a direct photograph of the Sun's future. It is better viewed as an example of how a star similar in broad evolutionary principles can take a less common path. Stellar mass loss is not always a quiet wind carrying gas away gradually. Companions can alter the process. A second star, brown dwarf, or perhaps a large planet can change when and how the envelope is removed. This makes stellar evolution less isolated than diagrams sometimes suggest. A textbook may show a single star moving through a sequence of stages. Real stars often have companions. Those companions exchange mass, disturb envelopes, remove angular momentum, merge or survive in changed orbits. A planet is much less massive than a star, but inside a red giant envelope, even a planet can release substantial orbital energy while spiraling inward. The question is whether that energy is enough to remove the envelope before the planet is destroyed. For KOI-55, researchers propose that more than one large planet may have participated. Two massive bodies moving through the envelope could contribute more energy than one. Their dense cores might then remain as KOI-55b and KOI-55c. Other possibilities have also been discussed. A single body could have broken apart. The remnants might have formed from debris after the envelope was expelled. The signals may have no planetary origin. Each explanation has difficulties, and none has been confirmed through direct observation. The current star gives us several firm facts around which those possibilities must fit. It is hot. It is compact. It has close to half the Sun's mass. It burns helium in its core. It has only a thin hydrogen layer. It pulsates in multiple modes. It was once a red giant and lost most of its envelope. Any convincing history for the system must explain those properties. It must also account for two possible bodies orbiting only hundreds of thousands of kilometers from the stellar center, assuming the signals are planetary. The phrase "a sun that already died once" can now be understood in a more precise way. KO-55 did not stop existing. It did not switch off. Its main sequence life ended. Its red giant form developed and disappeared, and its outer layers were removed. What remains is an exposed helium-burning core moving toward its eventual white dwarf state. The star is still evolving, but it has already experienced the event most likely to threaten any nearby planets. That event was not a distant flash observed from a safe orbit. The expanded stellar atmosphere reached the region where KOI-55b now travels. To understand how KOI-55b could have reached its present orbit, we have to return to a time when its star was much larger than it is now. The compact blue-white object at the centre of the system had expanded into a red giant, extending its outer atmosphere across the region where the proposed planet now travels. If KOI-55b existed before that expansion, it did not remain safely outside. It entered the star. This does not mean it struck a solid surface. A red giant has no hard outer boundary. Its gas becomes gradually denser as an object moves inward. A planet could begin its passage through material so thin that the first effects were modest, then encounter increasingly dense layers as the star continued to expand around its orbit. At the beginning, the planet may still have looked like a large gas giant. The original researchers suggested that KOI-55b could be the exposed core of a world that once contained far more mass. It might have resembled Jupiter, or it may have been several times more massive. A larger starting mass would improve its chances of influencing the star and surviving long enough to reach a close orbit. A gas giant is mostly hydrogen and helium. Those gases form a deep envelope surrounding a much denser interior. Beneath the visible clouds, pressure and temperature rise steadily. Farther down, hydrogen behaves less like an ordinary gas and more like a compressed fluid. Near the centre, the planet may contain a mixture of rock, metal, ice-derived compounds, and heavier elements accumulated during its formation. There is no simple solid floor beneath Jupiter's clouds, but there is still a large concentration of dense material near its centre. That dense interior is the part most likely to remain after the lighter outer layers have been removed. KOI-55b may be what was left when a much larger planet lost nearly all of its hydrogen and helium. As the star expanded, the planet would have begun moving through the red giant's atmosphere at orbital speed. Gas surrounding the planet would not have been moving in exactly the same direction or at the same speed. The difference would create drag. Drag removes energy from motion. A spacecraft moving through Earth's upper atmosphere gradually slows and drops into a lower orbit. A planet inside a red giant experiences the same basic principle on a much larger scale. As it pushes through stellar gas, it transfers some of its orbital energy to the material around it. The orbit then shrinks. The planet moves closer to the stellar core where gravity is stronger and the surrounding gas is denser. It speeds up as it falls inward, but the denser material creates even more drag. This produces a dangerous cycle. The planet loses energy, moves inward, encounters harsher conditions, and loses energy more quickly. The process is often described as a spiral in. The planet does not fall straight toward the centre. It continues orbiting while its orbital radius becomes smaller. Each trip carries it deeper into the star. Seen from outside, the red giant might not reveal the planet clearly at all. The world would be hidden beneath a broad layer of glowing gas. Inside, however, its motion could create shocks and turbulence. Stellar material would be pushed aside, compressed, heated, and pulled into a wake behind the planet. A moving boat leaves disturbed water behind it. A planet moving through a stellar envelope leaves a gravitational and hydrodynamic wake. The comparison is imperfect because the planet is travelling through hot plasma under powerful gravity, but the general effect is similar. Energy from the planet's motion spreads into the surrounding material. This transferred energy may have helped remove the star's envelope. Red giants hold their outermost gas relatively loosely compared with the dense central core. The envelope is enormous, but much of it lies far from the centre, where the gravitational binding is weaker. Pushing that material away still requires a substantial amount of energy. A planet spiralling inward can provide some of it. As the planet drops into a tighter orbit, gravitational potential energy is released. Part of that energy becomes heat and motion in the envelope. The outcome depends strongly on the planet's original mass. A small rocky planet would release relatively little orbital energy and would probably be destroyed before making a major difference. A massive gas giant could release far more. The original KOI-55 interpretation proposed that one or more giant planets may have taken part in removing the star's envelope, Their inward movement could have added enough energy to help drive gas away from the core. Once most of the envelope escaped, the star contracted into the hot subdwarf seen today. That would mean the planet did more than endure the star's transformation. It may have helped cause it. The star was damaging the planet while the planet was changing the star. The planet lost mass and orbital distance. The red giant lost its envelope. A system that once may have contained an ordinary-looking star and one or more giant planets was reduced to a compact stellar core with small bodies circling only a short distance away. This idea is plausible, but it is not a complete solution by itself. A planet that releases energy into a stellar envelope also has to survive the heat, pressure, tides, and physical impacts experienced during the inward journey. Removing the star's envelope is useful only if some part of the planet remains when the process ends. Heat would attack the planet from several directions. Hot stellar gas would flow around it. Shock waves would form in front of it. Friction and compression would raise the local temperature. Radiation from deeper and hotter parts of the star would add more energy. The planet's own outer atmosphere would expand as it heated. Once gas expands beyond the region where the planet's gravity can hold it securely, the surrounding flow can strip it away. Hydrogen and helium would be the first major layers to go. The loss may not have been smooth. Material could have been removed from the star-facing side, the trailing wake, and regions stretched by tidal gravity. Gas leaving the planet would mix with the red giant's envelope, becoming almost impossible to distinguish from the star's own material. The planet's radius would shrink as its envelope disappeared. Its mass would also decrease, weakening its gravity and making additional loss easier. The dense central region, however, would be much harder to remove than the outer gas. A rocky or metallic core has a smaller surface area relative to its mass, stronger internal binding, and a much higher density. Those properties offer some protection. They do not make it indestructible, but they allow it to endure conditions that would rapidly remove a broad atmosphere. The surviving core may not have been cool or solid. It could have become partly or completely molten. Its outer layers may have vaporized. Heavy elements could have escaped along with the lighter gases. Survival in this context does not mean remaining unchanged. It means that enough material stayed gravitationally connected to form a separate object after the encounter. Tidal forces would have created another serious threat. Gravity becomes weaker with distance, so the side of the planet facing the stellar core would feel a slightly stronger pull than the far side. At large distances, the difference might be small. Deep inside the red giant, it could become strong enough to stretch the planet. If the difference in gravity exceeded the planet's ability to hold itself together, the body could break apart. This is tidal disruption. It is related to the Roche limit, the distance inside which a fluid object can be torn apart by a more massive companion. A gas giant would be especially vulnerable because its outer layers are not rigid. The star's tidal pull could help remove the gaseous envelope even before heat and drag completed the job. The dense core would resist longer, but it too could be disrupted if it moved close enough. This possibility led to another proposed history for the KOI-55 system. Rather than beginning with two separate giant planets, the small bodies might be fragments of one massive planet. In that model, a single large gas giant entered the red giant's envelope and spiraled inward. Its motion helped expel much of the stellar gas. The planet's hydrogen and helium layers were stripped away, exposing a heavy central core. When that core reached a region of sufficiently strong tidal stress, it broke into several large pieces. Some fragments were destroyed or fell closer to the star, others remained in orbit, interacted with surrounding debris, and eventually settled into the short-period paths associated with KOI-55b and KOI-55c. This scenario explains why the two proposed worlds are both small and close together. Instead of two planets independently surviving nearly identical disasters, they could be pieces of the same original body. The concept is similar to the tidal disruption of a comet passing close to a planet or star, although the scale and composition are different. Comet Shoemaker Levy 9 was broken into fragments by Jupiter's gravity before those fragments struck the planet in 1994. A massive planetary core near a red giant's exposed centre could also be divided if the difference in gravitational pull became large enough. A broken planetary core would not produce two neat spherical worlds immediately. The initial fragments could follow crossing or unstable orbits. Smaller debris would form around them. Collisions might occur. Gas and dust left from the envelope could influence their movement. Over time, gravity would reshape the largest surviving fragments. Material with enough mass naturally settles toward a rounded form because gravity pulls uneven features inward. Interactions with the surrounding disk could move the bodies to slightly different orbital distances. The periods proposed for KOI-55b and KOI-55c are close to a 3-to-2 relationship. While the inner body completes roughly 3 orbits, the outer body completes a little more than 2. The match is not exact, but it is close enough to raise questions about whether migration and gravitational interaction affected the final arrangement. Orbital resonances can develop when bodies exchange small gravitational pulls repeatedly. If planets move through gas or debris and their orbits change gradually, they may become trapped near a simple period ratio. Similar processes are seen in young planetary systems and among moons. In the fragmented core model, the surviving pieces could have interacted with a temporary disk formed from stripped planetary material and stellar gas. Those interactions might have shifted their orbits and brought them near the observed ratio. This remains a proposal rather than an established history. There is no surviving record that tells us whether one planet entered the star or several. The system's present signals are too limited to reconstruct every stage. Even the planetary interpretation itself has been challenged. Several survival routes therefore remain open. KOI-55b may be the core of one giant planet, while KOI-55c is the core of another. Both could have spiraled inward separately and helped remove the envelope. Alternatively, both may be fragments of one more massive core. It is also possible that small bodies formed later from debris left around the hot subdwarf, although building Earth-sized objects so close to the star presents difficulties of its own. A planet formed after the red giant phase would avoid the need to survive engulfment. Material expelled from the star or released by a destroyed companion might settle into a disk. Dense fragments could collide and combine. The problem is that the environment around a newly exposed hot subdwarf is extremely energetic. Radiation heats and disperses material. The available time may be limited. Forming 2 substantial planets in very tight orbits would require enough heavy material to remain nearby and assemble efficiently. The original survival idea gained attention because it connected several unusual facts with one event. The close orbits, small estimated sizes, stripped star, and absence of a normal stellar companion could all be related to a common envelope interaction involving giant planets. Hot subdwarf stars are frequently found in binary systems. A companion star can remove the red giant's envelope through mass transfer or common envelope evolution. KOI-55 appeared to be isolated, which raised the question of how its envelope was lost. A large planet would be much fainter and harder to detect than a stellar companion. If one or more planets entered the envelope, they could offer an alternative removal mechanism. KOI-55b would then be both a surviving object and evidence for the missing companion responsible for shaping the star. The energy calculation is central to this explanation. A planet in a wide orbit has a certain amount of gravitational potential energy. When it moves into a much smaller orbit around the stellar core, the change releases energy. A more massive planet and a larger inward movement release more. Not all of that energy goes into ejecting the envelope. Some becomes local heat. Some moves gas without allowing it to escape. Some may be carried away in radiation. Models usually describe the uncertain efficiency with a parameter, rather than pretending every portion can be tracked exactly. If the efficiency is too low, a Jupiter-mass planet might not remove enough of the envelope before being destroyed. A more massive gas giant, perhaps several times Jupiter's mass, would have a better chance. Objects near the boundary between massive planets and brown dwarfs are particularly useful in this role because they contain much more orbital energy and stronger gravity. They can travel deeper before losing all of their mass. At some point, however, the original object becomes so massive that calling it a planet becomes less clear. The proposed ancestor of KOI-55b need not fit neatly into the categories used today. It may have been a very massive planet, a low-mass brown dwarf, or one member of a multiple planet system. What matters for the survival model is that it had enough mass to enter the envelope, release energy, and leave a dense remnant. The passage probably accelerated near the end. The outer portions of a red giant are diffuse, so early drag may have been relatively weak. Deeper layers are denser. Once the planet reached them, orbital decay could proceed much more quickly. At the same time, the envelope itself was changing. Energy released by the planet would cause gas to expand. Some material could be ejected completely, reducing the density around the orbit. The planet's inward motion and the star's outward loss were therefore connected. If the envelope thinned quickly enough, drag would weaken before the core was destroyed. The planet could then stop spiraling inward and remain in a short orbit around the exposed stellar core. This provides a possible escape mechanism. The planet did not need to withstand the red giant indefinitely. It needed to survive until its own orbital energy helped remove the gas responsible for dragging it inward. Timing would be crucial. Remove the envelope too slowly, and the planet falls deeper or breaks apart. Remove it too early, and the object may remain farther out than the observed orbit. The present distance would record where the interaction ended. KOI-55b's current orbit is only around 900,000 kilometers from the center of the star, close to the scale of the Sun's radius. During the red giant phase, that region lay deep inside the expanded atmosphere. Reaching it would require a major loss of orbital energy. The planet may have crossed millions or tens of millions of kilometers while embedded in the star. Depending on the red giant's former size, it could have begun at an orbit comparable to that of Mercury, Earth, or even farther out before being captured by the expanding envelope. The exact starting distance is unknown because the star's original mass and planetary system are not fully known. Mass loss from the star would tend to widen planetary orbits, while drag inside the envelope would pull them inward. Before engulfment, tidal interactions could also change the orbit. As a red giant expands, it raises tides on nearby planets. Those tides can transfer angular momentum and gradually draw a close companion inward even before the stellar surface reaches it. A planet that appears temporarily outside the atmosphere may already be moving toward engulfment. Once surrounded, the planet would have little opportunity to reverse course. Gas drag acts in the direction opposite its orbital motion. Unless the envelope is expelled, the spiral continues. The planet's own mass loss would complicate this movement. A lighter body interacts differently with the surrounding gas and has less energy available to release. As its outer layers disappear, it becomes less able to help eject the envelope. The survival process therefore contains a race. The planet must deposit enough energy while it is still massive. The envelope must be removed before the remaining core is evaporated or torn apart. Some calculations suggest that Jovian planets can lose extensive mass inside a giant star while denser remnants survive. Other studies find that many substellar companions would either remain largely intact or be destroyed, depending on their mass and how deeply they travel. The result changes with the structure of the star and the assumptions used for drag, evaporation, and energy transfer. There is no single rule stating that every engulfed planet dies or every massive planet survives. A low-mass world entering dense layers is in serious danger. A heavier and denser object may endure. A planet caught only in the outer envelope experiences a different event from one dragged close to the stellar core. KOI-55b, if it is a planetary remnant, represents an extreme case. It would have travelled unusually deep and lost an enormous fraction of its original material. Calling it a survivor does not imply that most of the original planet survived. The remnant may contain only a small percentage of the starting mass. Suppose the planet began with several hundred Earth masses, comparable to Jupiter or larger, and ended with less than one Earth mass. More than 99% of it could have disappeared. Nearly all of the atmosphere, most of its fluid interior, and perhaps part of the heavy core would be gone. The remaining object might be rich in iron, silicate rock, or other dense materials. Its composition would depend on how the original planet formed and how thoroughly it was stripped. A gas giant can contain heavy elements mixed through its interior rather than stored in one sharply defined core, so the remnant might not resemble a simple exposed metal sphere. High pressure inside the original planet could also have produced materials that changed as the pressure was released. Once the outer mass disappeared, the remaining core would expand, melt, separate into layers, or lose additional volatile compounds. During the red giant interaction, the core may have been surrounded by material hotter than many stellar surfaces. After the envelope left, it faced the newly exposed hot subdwarf. The immediate threat changed, but it did not vanish. The dense stellar gas was no longer dragging the planet inward. Instead, ultraviolet radiation from the compact star began heating the exposed remnant directly. Any atmosphere that remained would have been vulnerable to rapid escape. A strong planetary magnetic field has been suggested as one possible source of protection. A magnetic field can influence charged particles and interact with a stellar wind. In some models, a rapidly rotating remnant with a conducting interior might support a field stronger than Earth's. Magnetic protection would not create a comfortable atmosphere or block the intense heat. It might reduce certain forms of erosion and help the planet retain mass for longer. The effectiveness would depend on the field's strength, structure, and interaction with the star's radiation and plasma. The planet is likely tidally locked now, but during the violent interaction, its rotation could have changed repeatedly. Tides would work to synchronize its spin with its shrinking orbit. If the remnant ended with a rotation period of only a few hours, its rapid spin might have affected its internal dynamo. Even without magnetic shielding, a dense core can survive longer than a gas envelope. Heavy atoms require more energy to remove, and the planet's gravity still holds material near the surface. Escape would continue, but not necessarily quickly enough to erase the object immediately. Immediately is another word that astronomy uses differently from ordinary conversation. A planet that loses its atmosphere in 1 million years is being stripped rapidly by planetary standards. It would still outlast every human civilization recorded so far. The current hot subdwarf phase lasts long enough for evaporation to matter. If KOI-55b has existed in its present orbit throughout much of that period, it must either lose mass at a manageable rate or have begun considerably larger than it is today. The reported size and mass are model dependent, so the exact amount remaining is uncertain. If the original brightness signals have another cause, none of these survival calculations describes a real planet. That uncertainty should remain present without interrupting every sentence. The value of the system lies partly in testing these models. If close planetary remnants around hot subdwarfs are confirmed elsewhere, it would strengthen the argument that giant planets can help eject red giant envelopes. If such detections repeatedly disappear under closer analysis, astronomers would need to be more cautious about identifying planetary signals among stellar pulsations. Other evolved stars do have close substellar companions, including brown dwarfs and massive planets. Their existence shows that engulfment does not always end in complete destruction. The survival of an Earth mass remnant at the distance proposed for KOI-55b would push that principle into a much more extreme range. There may also be planets farther from the star that avoided engulfment. A red giant loses mass, weakening its gravitational hold and allowing distant orbits to expand. Such planets could remain around the resulting white dwarf or hot subdwarf at wide separations. KOI-55b, by contrast, belongs to the population that moved inward rather than outward. It may have traded nearly all of its material for a place close to the stellar core. That history changes how we should picture the object. It is not simply an Earth-sized planet placed beside a hot star. It may be the final dense portion of a former giant, shaped by a prolonged passage through stellar gas. Every major property could be a result of that journey. Its small size may come from stripping. Its close orbit may come from drag. Its possible companion may be another survivor or a fragment. The host star's missing envelope may partly reflect the energy released during the inward spiral. Even the planet's present temperature follows from where the interaction stopped. Had it remained farther away, it would receive less radiation. Had it moved closer, it might have crossed the tidal disruption boundary, or fallen into the star. Its current orbit may occupy the narrow region where the envelope disappeared before the remnant did. The survival story is therefore not one of a planet resisting every force without changing. It is a story of continuous loss. The original world may have surrendered its atmosphere, much of its mass, its old orbit, its rotation, and perhaps its identity as a gas giant. Only the most tightly bound material may have remained. That material now travels around the exposed core of the star in less than 6 hours, still facing conditions capable of removing it piece by piece. Once the stellar envelope had cleared, the scene would have changed quickly. The small remnant was no longer buried in red giant gas. The compact star appeared directly in its sky, emitting intense, visible and ultraviolet radiation. The boundary between the surface and the atmosphere would be difficult to define because KOI-55b may be hot enough for the material beneath it to enter several physical states at once. On Earth, the ground is solid, the air is gas, and the distinction between them is usually obvious. On this planet, the upper layers could be molten, while material from those layers continuously boils into a dense mineral vapor. Higher up, the vapor may be broken into individual atoms, ions, and free electrons. NASA gives KOI-55b an estimated average temperature of about 6,800 degrees Celsius, or approximately 12,000 degrees Fahrenheit. That corresponds to a little over 7,000 Kelvin. The number is not based on a thermometer placed on the ground. It is an estimate derived from the planet's distance from its star, the star's temperature and size, and assumptions about how the planet absorbs and releases energy. Those assumptions matter. A planet can reflect part of the light that reaches it. It can distribute heat through an atmosphere or molten interior. Its day side can be much hotter than its night side. Different parts of the surface may therefore have very different temperatures. KOI-55b has not been observed in enough detail to produce a proper temperature map. Astronomers cannot yet point to one hemisphere and state exactly how hot it is. The value of 6,800 degrees Celsius should be treated as a broad estimate of the conditions expected from the published planetary model. Even allowing for uncertainty, the temperature is far beyond the range normally associated with planets. Venus, the hottest planet in our solar system, has a surface temperature of about 465 degrees Celsius. That is hot enough to melt lead. KOI-55b may be more than 14 times hotter when the temperatures are compared in degrees Celsius. The comparison is not physically perfect because Celsius does not begin at absolute zero, but it gives a useful sense of scale. Venus would be an extremely hot environment for a spacecraft. Beside KOI-55b, it would be the cooler option, which is not a sentence Venus gets to hear very often. Ordinary lava on Earth is usually between about 700 and 1,200 degrees Celsius. Some industrial furnaces operate at temperatures above 1,500 degrees. Iron melts at around 1,538 degrees Celsius and boils at close to 2,862 degrees at standard atmospheric pressure. Tungsten, famous for having the highest melting point among pure metals, melts at roughly 3,422 degrees Celsius. KOI-55b's estimated temperature is well above all of those values. A tungsten landscape would not provide a durable solution. It would melt and, depending on pressure, begin entering the gas phase. Building a shelter from the strongest familiar metal would therefore be a short project, followed by an even shorter inspection. The visible surface of the Sun has a temperature near 5,500 degrees Celsius. This outer layer, called the photosphere, is the region from which most of the sunlight visible to human eyes escapes. KOI-55b's estimated temperature is about 1,300 degrees higher. This is the specific sense in which the planet is described as hotter than the surface of the Sun. It is not hotter than the Sun's core, where the temperature reaches about 15 million degrees Celsius. It is also not hotter than every region of the solar atmosphere. This Sun's corona reaches temperatures of more than 1 million degrees, even though it is extremely thin. The comparison concerns the bright layer we normally think of when we look at an image of the Sun. A planet whose average temperature may exceed that layer is unusual enough without asking it to compete with the solar core. KOI-55b is not a star. Its high temperature does not mean nuclear fusion is occurring throughout its interior. Stars shine because immense pressure in their cores allows light nuclei to combine and release energy. A small rocky object does not have enough mass to create those central conditions. The planet receives its heat from outside. Its host star has an effective surface temperature of about 27,700 Kelvin and appears enormous from the planet's orbit. KOI-55b absorbs part of that radiation and then emits energy of its own because all hot matter radiates. A heated object changes its visible appearance as its temperature rises. A piece of metal first glows dull red, then becomes orange, yellow, and eventually white. At temperatures around 7,000 Kelvin, an ideal thermal emitter would release a large amount of visible light and would appear white with a bluish component. KOI-55b could therefore glow under its own heat. It would not merely reflect its star's light like the Moon reflects sunlight. Its surface and any surrounding vapour would emit thermal radiation, strongly enough to add a small amount of light to the system. That changing glow was central to the original detection claim. The proposed planet did not produce a clear transit across the star. Researchers instead identified repeated brightness variations that they interpreted as the hot side of the planet moving in and out of view. When the hottest hemisphere faced Earth, the system would appear very slightly brighter. When that hemisphere turned away or passed behind the star, the total brightness would decrease. The change was extremely small because the star remained far brighter than the planet. This interpretation assumes that KOI-55b has a strong contrast between its star-facing side and its opposite side. Such a contrast is likely if the planet is tidally locked and cannot move heat efficiently around its surface. A tidally locked world turns once during each orbit, keeping approximately the same hemisphere directed toward the star. One region receives constant radiation. The opposite hemisphere never sees the star directly. Between them is a permanent transition zone. The point facing directly toward the star is called the substellar point. It would receive the most concentrated heating. Moving away from that point, the star would appear lower in the sky, and the incoming energy would strike the surface at a shallower angle. If the planet has little atmosphere, the substellar region could be much hotter than the night side. Rock absorbs the radiation, heats rapidly, and releases energy back into space. Without thick moving air or a deep circulating ocean, relatively little heat would reach the dark hemisphere. KOI-55b may have a molten surface capable of carrying heat through flowing material. Its interior may also conduct energy from one region to another. These processes could reduce the contrast, but they would probably not make the temperature uniform. The star-facing side may be covered by a deep magma layer, while cooler material could exist farther from the substellar point. The word cooler is relative. A region thousands of degrees below the hottest point could still be hot enough to melt or vaporize most common rocks. At the estimated average temperature, the idea of a normal magma ocean becomes incomplete. Magma is liquid rock. Heat it further, and the liquid begins producing mineral vapor. At sufficiently high temperatures, the vapor can become the dominant visible layer. Earth's atmosphere is mainly nitrogen and oxygen. because those gases are available and stable under terrestrial conditions. A mineral atmosphere above KOI-55b would come directly from heated planetary material. Its ingredients would depend on the composition of the underlying rock or metal. Models of hot rocky planets predict gases containing sodium, potassium, iron, magnesium, silicon monoxide, atomic silicon, atomic oxygen, and molecular oxygen. As temperatures rise, larger molecules become unstable. Collisions break them apart faster than they can remain assembled. Water would not survive as water. Carbon dioxide would not remain comfortably intact. Complex compounds would be split into simpler molecules and individual atoms. At the highest levels, ultraviolet radiation from the star would remove electrons from those atoms, producing ions. The result could be a mineral vapor atmosphere with a partially ionized upper region. It would contain some of the same elements found in Earth's crust, but not arranged into soil, stone, or breathable gas. It would be geology converted into weather. Pressure would influence every phase change. The familiar melting and boiling points quoted for materials are usually measured at specific pressures. On a planet with a thin atmosphere, substances can vaporize at lower temperatures. In a dense atmosphere, they may remain liquid at higher temperatures. KOI-55b's atmospheric pressure is unknown. If the planet is losing material rapidly, its gas may not form a stable, thick envelope. Vapor could be created near the surface and then flow outward, producing an atmosphere that is continuously replaced rather than permanently stored. The hottest material would rise and expand. As it moved away from the surface or toward the night side, it would cool. Some elements might condense into droplets or grains. Those particles could fall back, move around the planet, or be carried away into space. This creates the possibility of a rock cycle unlike the one on Earth. Here, rocks are broken down by water, carried as sediment, buried, melted, and returned through volcanism over millions of years. On KOI-55b, surface material may boil into the atmosphere, travel a short distance, condense, and fall back much more quickly. There could be clouds, but they would not be clouds of water. Depending on local pressure and temperature, condensed mineral material might gather into droplets or particles. Iron, aluminium-rich compounds, calcium-bearing material and silicates could all behave differently as the gas cools. At 6,800 degrees Celsius, however, the dayside may be too hot for many forms of mineral condensation near the surface. Cloud formation would be more likely at higher altitudes, near the transition region, or on the night side. The composition would also change over time. More volatile elements escape first because they enter the gas phase more easily. Sodium and potassium may be removed relatively quickly. The remaining surface becomes enriched in materials that are harder to vaporize. This process is called fractional vaporization. It is similar in principle to boiling a mixture and removing the components that evaporate most readily. The material left behind no longer has the same composition as the starting mixture. If KOI-55b has been heated for millions of years, its outer layer may be heavily processed. It may not resemble Earth's mantle, even if it began with similar rocky ingredients. Easier to remove elements could already be depleted. A remnant that began as the core of a gas giant could have an even more unusual composition. It might contain a large fraction of heavy elements, including iron and materials formed under high pressure. Once the outer planet was removed, those layers would be directly exposed to much lower pressure and intense radiation. The surface might therefore contain metal-rich melts, silicate melts, or a mixture that changes with depth. Dense iron could sink while lighter silicate material rises, although constant evaporation and strong tides may disturb any simple layering. If enough of the silicate portion were removed, the planet could eventually expose an iron-rich interior. Some models of evaporating rocky worlds suggest that a planet near the end of its mass loss may resemble a naked metallic core. KOI-55b's estimated mass is still large enough that its gravity would hold tightly to much of its dense interior. Heavy atoms move more slowly than hydrogen atoms at the same temperature because they have greater mass. That makes them more difficult to remove through ordinary thermal escape. the temperature remains high enough to produce a substantial vapor supply, and the star provides intense ultraviolet radiation. Atoms in the upper atmosphere can absorb that energy, become ionized, and move fast enough to escape. The planet may therefore lose material through several related processes. Direct heating vaporizes the surface. Pressure gradients drive gas upward and away from the hottest region. Ultraviolet radiation heats and ionizes the upper atmosphere. The star's gravity and radiation pressure then influence the escaping flow. Any stellar wind would add another effect. A stellar wind is a stream of charged particles moving outward from a star. The wind from KOI-55's hot subdwarf host could interact with ions released by the planet, carrying them away or shaping them into a trail. A magnetic field could redirect some charged particles, but there is no evidence that KOI-55b has one. Even a strong field would not prevent the surface from absorbing light and heating. It might change the pattern of atmospheric escape rather than stopping it. Material leaving the planet may produce a tail pointing partly away from the star and partly behind the planet's orbit. Similar tails have been proposed for other disintegrating rocky exoplanets, where clouds of dust create changing transit shapes. Near KOI-55b, the heat may make dust formation difficult close to the planet. Solid grains cannot survive where their temperature exceeds the point at which they sublimate. Escaping vapor would need to travel far enough and cool enough before stable particles could form. This means the outflow might remain mostly gaseous and ionized near the orbit. Farther away, some material could condense. The exact structure would depend on the rate of escape, the star's radiation, and the chemistry of the gas. NASA describes the planet as evaporating, but the current rate is not directly measured. There is no confirmed observation showing how many kilograms leave the planet each second. The description follows from the expected effect of extreme heating on a small rocky body. A planet with 44% of Earth's mass is not easily erased. Earth has a mass close to 6 sextillion metric tons. Even a fraction of that is an enormous amount of material. Removing the entire object would require continuous loss over a long period. The rate can also change dramatically as the planet becomes smaller. A lower mass body has weaker gravity, making escape easier. Its surface may then begin losing material faster. Some evaporating planets could spend a long time changing slowly before entering a brief final period of rapid destruction. KOI-55b may not be in that final period. It may have maintained a roughly similar mass for millions of years, or it may be shrinking significantly. Without a direct mass loss measurement, both the present rate and the remaining lifetime are uncertain. The surface conditions would also depend on whether the planet has a deep interior capable of transporting material upward. If only a thin outer layer melts, evaporation could leave behind a resistant crust enriched in high-temperature compounds. At 6,800 degrees Celsius, forming a lasting solid crust on the day side seems unlikely. Even highly refractory materials would struggle to remain solid. The night side might allow some material to freeze, but circulation could return it toward hotter regions. A fully molten or partly vaporized exterior could circulate continuously. Heating makes material expand and become less dense. Cooler material becomes denser and sinks. The combination can produce convection within the molten layer. The strong pull of the nearby star may also create tidal deformation. If the orbit is not perfectly circular, or if the planet's rotation is not fully synchronized, the changing distortion can generate internal friction. That process, known as tidal heating, could add energy beneath the surface. Stellar radiation probably dominates the planet's present heating, but tidal energy may still affect the interior. It could help maintain melting on the night side or drive movement below the surface. The planet's shape may not be perfectly spherical. Tidal forces could stretch it slightly toward the star. A molten object responds more readily to that pull than a rigid one. The highest and lowest points would be determined less by mountains and more by gravity, rotation, and the shape of the liquid exterior. Mountains, craters, and cliffs would have difficulty surviving. A crater formed by an impact would quickly fill with molten material or soften as the surrounding rock flowed. A mountain would slump because its heated material lacked the strength to hold a tall structure. Meteor impacts would still occur, but many incoming objects would vaporize before reaching the lower atmosphere. Larger bodies could strike the surface and release additional energy, although distinguishing impact heating from the already extreme background would be difficult. There may be no recognizable geology in the usual sense. Plate tectonics requires solid plates moving over a softer interior. Weathering requires stable surface material. Erosion normally involves wind, liquid, ice, or repeated temperature changes acting on solid rock. KOI-55, B could instead have large-scale currents in molten material, continuous evaporation, chemical separation, and deposition on the cooler side. Its geology and atmosphere would function as parts of the same system. Standing on such a surface is impossible for familiar matter, but imagining the view can still help explain the physics. An observer would need to be protected by technology far beyond anything available. Ordinary spacecraft alloys would fail, electronics would be destroyed, a heat shield designed for brief atmospheric entry could not endure continuous exposure. The observer would see the host star filling a wide area of the sky. It would appear blue-white and painfully bright. The surface around the observer might also glow because its temperature is high enough to emit visible light. If a mineral atmosphere were dense, the view could be obscured by glowing gas. Light from the star would be absorbed and re-emitted at different wavelengths. Certain atoms might create strong colours at particular wavelengths. Although the combined brightness could appear mostly white, there would be no cool shadow. Blocking direct starlight would reduce incoming radiation, but the surrounding surface and atmosphere would still emit intense heat. The night side would offer less direct radiation, yet it might remain bright from molten material and transported energy. Sound would depend on the atmosphere. A sufficiently dense mineral gas could carry pressure waves, but no human ear could operate there. The gas might move at very high speed from the day side toward the night side as it responded to pressure differences. Near the substellar point, vapor pressure would be highest because the surface is hottest. Gas would expand outward toward cooler areas. This could create strong winds flowing away from the center of the illuminated hemisphere. When the gas reached cooler longitudes, some components would condense. The atmosphere would lose pressure, drawing more vapor from the hot side. Material could then return through surface flows, deeper magma currents, or gradual movement along the ground. The result might be a global circulation system driven by the evaporation of rock. It would be less like Earth's weather and more like an industrial distillation process operating across an entire planet. Different elements would complete that circulation at different distances. A substance with a high condensation temperature might fall out near the edge of the day side. More volatile material could travel farther onto the night side before condensing. Over time, this could create regions with different compositions. The hottest area might be depleted in easily vaporized elements. Cooler zones might accumulate deposits carried from the day side. The night hemisphere could contain layers of condensed minerals that are repeatedly buried or drawn back into circulation. None of these features has been observed directly on KOI-55b. They are possible consequences of applying models of lava planets and mineral atmospheres to a far more extreme temperature. The real object could differ because its composition, pressure, and evolutionary history are unknown. It is also possible that the published temperature overstates the conditions in some locations. A highly reflective surface would absorb less energy. Efficient circulation would spread heat across a larger area. A planet that radiates energy effectively could remain cooler than a simple estimate suggests. A highly reflective surface is difficult to maintain when the surface is molten or vaporized, and the star provides strong ultraviolet light. Many hot rocky materials absorb a substantial fraction of incoming radiation. Even a major reduction from the quoted temperature would leave KOI-55b far hotter than ordinary lava planets. The opposite is possible as well. The substellar point may exceed the average estimate if heat remains concentrated on the day side. Local temperatures could be higher than 6,800 degrees Celsius while the night side remains below it. At those temperatures, thermal ionization becomes increasingly important. Collisions can remove electrons from atoms without requiring every ionization event to come from ultraviolet light. The atmosphere begins to share some properties with plasma. Plasma is often called the fourth state of matter. It is a gas containing charged particles whose behavior can be influenced strongly by electric and magnetic fields. Stars are made mostly of plasma, but a planet can develop plasma in its atmosphere without becoming a star. KOI-55b may therefore possess a molten or vaporizing planetary interior, beneath an atmosphere that becomes increasingly plasma-like with altitude. The transition would not occur at one clean level. Temperature, pressure, and ionization would change gradually. The escaping material could form an electrically conducting environment, linking the planet with the star's magnetic field. Currents might flow through the plasma. Charged particles could be guided towards certain regions of the planet or carried along magnetic structures. Such interactions occur between Jupiter and some of its moons. Io, for example, releases material that becomes ionized and forms a torus around Jupiter. KOI-55b's environment would be much hotter and more compact, but the comparison shows that a small body can supply charged material to the space around a larger object. If KOI-55b releases enough gas, some of it could spread around the star along the planet's orbit. Instead of a neat, isolated atmosphere, the system might contain a thin ring or cloud of planetary material. Detecting such material would be valuable because its spectrum could reveal composition. Absorption lines from metals or ions might show what the planet is losing. No secure detection of such an outflow has yet provided that information for KOI-55b. Future observations would be difficult. The system is distant, the star is faint, and the proposed planet sits extremely close to it. Separating planetary light from stellar pulsations is already challenging. Measuring individual chemical signatures from the planet would require exceptional sensitivity and careful modelling. The host star's ultraviolet output adds another obstacle because it alters the escaping atmosphere. The material detected far from the surface may not preserve the same chemical form it had when it left. Molecules can be dissociated, atoms can be ionized, and radiation pressure can sort particles according to how they absorb light. Even so, the surface models help explain why the original brightness signal was considered planetary. A body heated to several thousand Kelvin can emit enough visible light to produce a repeating variation as it circles its star. The more intense the day-side heating, the larger that variation could become. There is a complication. The host star pulsates at many frequencies, and those pulsations can imitate periodic planetary signals. Later research suggested that the observed frequencies may arise from combinations of stellar oscillations, rather than from the hot faces of orbiting worlds. For that reason, every description of KOI-55b's surface remains conditional. If the object exists with the published properties, these are the conditions expected from known physics. If the light variation belongs entirely to the star, then the surface is a useful model of an extreme hypothetical world rather than a confirmed landscape. The uncertainty does not change the basic scientific lesson. Rocky material placed near a star this hot would not behave like ordinary ground. It would melt, vaporize, separate chemically, become partly ionized, and escape. The distinction between a planet and its atmosphere would be continually reshaped by heat. KOI-55b would not have a permanent coastline around a stable lava ocean. The level of the melt could change as material evaporated and condensed. There may be no stable reference point from which to measure the surface. Its exterior would be a working boundary between the dense planet below and space above. Atoms would enter that boundary as rock, pass through it as liquid or vapour, and some would leave the planet entirely. This continuous loss does not require a dramatic explosion. The planet may simply become lighter over time. Each orbit exposes it to another cycle of heating, radiation, circulation and escape, although the word cycle is slightly misleading on a tidally locked world because the same region remains under the star. A location on the day side would experience no sunrise or sunset. Its heating would continue without interruption. The sky would not darken every few hours even though the planet completed a full orbit. The star would remain in approximately the same position above the surface. Its surface conditions and its orbit cannot be separated. The extreme heat exists because the planet travels so close to the star. The tidal locking exists because the orbital distance is so small. The possible atmospheric escape, permanent dayside, powerful tides and rapid motion all come from the same compact arrangement. A year on KOI-55b lasts about 5 hours, 45 minutes and 45 seconds. That is the time required for the planet to travel once around its star and return to the same position in its orbit. On Earth, a year contains changing seasons, school terms, holidays, birthdays, tax deadlines, and enough time to forget several passwords. On KOI-55b, the entire year fits comfortably between midnight and breakfast. During one Earth day, the planet completes a little more than 4 orbits. In one Earth year, it circles its star about 1,500 times. A person attempting to count each orbit would need to pay close attention and give up most other activities. The short period is not caused by the star pulling the planet around like an object attached to a string. KOI-55b remains in orbit because it is moving sideways fast enough to keep missing the star as gravity pulls it inward. This is the same principle that keeps Earth around the Sun and the Moon around Earth. The difference is the scale. KOI-55b is thought to orbit about 0.006 astronomical units from the centre of its star. 1 astronomical unit is the average distance between Earth and the Sun, close to 150 million kilometres. A distance of 0.006 astronomical units is approximately 898,000 kilometres. That is only a little more than twice the average distance between Earth and the Moon. Placing a planet less than 900,000 kilometres from the centre of a star sounds impossible until the size of the star is considered. KOI-55 is no longer a swollen red giant. It has lost most of its outer layers and contracted into a compact hot subdwarf with a radius of roughly 141,000 kilometres. The planet therefore travels outside the star's present visible surface. Its orbit lies about 6.4 stellar radii from the centre, leaving a gap of roughly 756,000 kilometres between the visible surface and the planet's average orbital path. That gap is enormous by human standards. It would take ordinary spacecraft a long time to cross. Within a planetary system, it is extremely narrow. Mercury never comes closer than tens of millions of kilometres to the Sun. KOI-55b moves through a region that would lie well inside the Sun if its star were replaced by ours. The planet must travel at roughly 270 kilometres per second to maintain such a tight orbit. Earth travels around the Sun at about 30 kilometres per second. KOI-55b may therefore move approximately 9 times faster than Earth does in its orbit. At that speed, the planet could cross the width of Earth in less than a minute. It could cover the average distance between Earth and the Moon in around 24 minutes. It would travel from London to New York in about 20 seconds, though arriving at either city would remain difficult because the planet is not equipped with brakes, airports, or a surface that permits luggage. Despite this tremendous motion, an object resting on the planet would not feel a constant force pushing it backward. The ground, the atmosphere, and everything else on the planet would share the same orbital velocity. Constant speed is not felt in the same way that acceleration is. Passengers on a smooth aircraft do not feel its full forward speed once it is cruising steadily. They notice takeoff, turbulence, turns and landing because those involve changes in velocity. KOI-55b's orbit is curved, so its direction changes continuously, but gravity provides the inward acceleration that keeps the planet following that path. The planet is not fighting gravity. Its orbit is the result of gravity. A common question about close planets is why they do not fall into their stars. An orbiting object is falling continuously. It simply has enough sideways speed that the curved surface of the star remains below it. Remove some orbital speed, and the path becomes lower. Remove enough, and the planet will eventually enter the star. Give the object more speed, and it can move into a wider orbit or escape the system altogether. KOI-55b occupies a narrow balance between inward gravity and rapid sideways motion. That balance probably developed during the red giant interaction. The planet, or the larger object from which it came, lost orbital energy while moving through stellar gas. Its path shrank until the envelope was expelled. Once the dense surrounding gas disappeared, the major source of drag disappeared with it. Space around the present hot subdwarf is not completely empty. The star can emit radiation and charged particles, while the planet may release vaporized material. This environment is still far less dense than the interior of a red giant envelope. Ordinary gas drag no longer pulls the planet inward at anything like the earlier rate. Its orbit may therefore remain stable for a long time, even though it looks alarmingly close. Stable does not mean unchanging forever. Tidal interactions, stellar evolution, mass loss, and gravitational effects from the proposed companion could slowly alter the path. It means the planet is not expected to fall into the star during the next few orbits, simply because the distance looks uncomfortable. The orbital period also determines how frequently the planet presents different sides to a distant observer. The original Discovery interpretation relied on tiny changes in the total light from the system. As KOI-55b moved around the star, astronomers proposed that its intensely heated hemisphere became more or less visible from Earth. When the full hot side faced us, the planet contributed slightly more light. When the cooler side faced us, it contributed less. If the planet passed behind the star from our viewpoint, its light would disappear briefly into the much brighter stellar signal. The entire pattern repeated every 5.7625 hours. A regular repetition is important because random noise does not usually maintain the same period and phase for long. Astronomers search for signals that return on a dependable schedule. The difficulty is that KOI-55 itself pulsates on several schedules. Its surface brightness changes as different oscillations move through the star. Combinations of those oscillations can produce additional frequencies, including patterns that may resemble orbital modulation. This is why the 5.76-hour signal remains controversial. Its regularity encouraged a planetary explanation, but regularity by itself is not proof of a planet, when the star is also a precise natural oscillator. Assuming the signal does belong to KOI-55b, the planet is almost certainly affected by tidal locking. A close star does not pull every part of a planet equally. The near side feels a slightly stronger gravitational attraction than the far side. This difference stretches the planet and creates a tidal bulge. If the planet rotates faster than it orbits, the bulge does not remain perfectly aligned with the star. Internal friction prevents the material from responding instantly. The star's gravity then pulls on the offset bulge, gradually changing the planet's rotation. Rotational energy is converted into heat, and the spin slows. Given enough time, many close bodies reach a state in which one rotation takes the same amount of time as one orbit. This is synchronous rotation, commonly called tidal locking. The Moon is tidally locked to Earth. It rotates once every time it travels around us, which is why nearly the same hemisphere faces Earth continuously. The far side of the Moon is not permanently dark. It receives sunlight during part of each lunar orbit. It is called the far side because it points away from Earth. KOI-55b would be locked to its star rather than to a planet. One hemisphere would remain directed toward the star, while the other would remain turned away. its rotation period would be the same as its year, about 5 hours and 46 minutes. This creates an unusual definition of a day. If a day means one full rotation relative to distant stars, it lasts just under 6 hours. If a day means the interval from one sunrise to the next, many places on the surface may never experience one. At the substellar point, the star would remain almost fixed overhead. On the opposite side, it would never rise. Along the boundary between the hemispheres, it would remain near the horizon. Small movements could still occur. An orbit that is slightly elliptical would make the planet travel faster when closer to the star and slower when farther away. If its rotation remained nearly uniform, the star could appear to shift back and forth in the sky. A tilted rotational axis or gravitational disturbance from another body could add more movement. The general arrangement would remain unlike Earth's daily cycle. There would be no regular morning, afternoon, sunset and night caused by rotation. The illuminated hemisphere would experience continuous stellar heating. A year would pass without the star moving around the sky in the familiar way. The planet would complete an entire orbit, while the surface beneath the substellar point continued facing inward. This makes the phrase 6 hours to circle a dying star sound calmer than the physical reality. The planet moves hundreds of kilometers every second, yet the star may appear almost stationary to an observer on the ground. The view would be dominated by the star's size. Based on the published stellar radius and orbital distance, KOI-55 could appear around 18 degrees wide in the planet's sky. The Sun appears about half a degree wide from Earth. The host star might therefore look more than 30 times wider than the Sun does to us. It would cover well over 1,000 times as much apparent sky area. Holding up a thumb would not come close to hiding it. Light would take only about 3 seconds to travel from the star to the planet. Sunlight takes a little more than 8 minutes to reach Earth. KOI-55b receives information about changes at its star with almost no delay on human timescales. Any pulse of ultraviolet radiation, change in stellar output, or disturbance in the nearby plasma environment would reach the planet quickly. Material expelled at slower speeds would take longer, but the system is so compact that stellar activity could affect the planetary environment almost immediately compared with most orbital arrangements. The host is sometimes described as a dying star, although it is more accurate to call it an evolved star. It has already passed through the red giant phase and is currently burning helium in its core. It will eventually become a white dwarf, but it has not stopped producing energy through nuclear fusion. For KOI-55b, the distinction offers no relief. The star is compact, extremely hot, and rich in ultraviolet radiation. Its present stage may continue long enough to expose the planet to severe heating for millions of years. There is no habitable zone in any practical sense at the planet's current orbit. The phrase, "life in an impossible orbit," does not suggest organisms living there. It refers to the physical experience the orbit would impose on any object trying to remain intact. Life as we know it depends on complex molecules, stable chemical bonds, energy differences that can be controlled, and environments where matter can maintain organized structures. At several thousand degrees, complex biological molecules cannot survive. Proteins, DNA, cell membranes, and liquid water would be dismantled into simpler components long before reaching the surface. Even speculative forms of life would face the basic problem that atoms are being separated from molecules, and, in some regions, electrons are being separated from atoms. A system cannot easily preserve complicated biological organization when its chemical structures are repeatedly broken apart by heat and radiation. The planet may have no stable surface pressure, no enduring liquid other than molten rock or metal, and no regular day-night cycle. There is also little reason to expect the temperature to fall into a moderate range anywhere near the ground. The night side is sometimes imagined as a refuge on tidally locked planets. On a cool world with a thin atmosphere, the dark hemisphere could become extremely cold. KOI-55b begins with so much incoming energy that the night side may remain hot through atmospheric circulation, molten flow, internal conduction, and tidal heating. Even if part of that hemisphere cooled enough for some material to solidify, it would not become a comfortable region. Mineral vapour could move from the day side and condense there. The ground might be continuously buried, remelted, or drawn back toward hotter regions. The 6-hour orbit also leaves little room for a large moon. A planet can retain a satellite only within a region where its own gravity dominates over the star's tidal pull. This region is called the Hill sphere. Close to a star, the Hill sphere becomes small. KOI-55b's low mass and tiny orbital distance would give it only a narrow gravitational territory. A moon would need to orbit very close to the planet, but moving too close creates tidal and structural problems of its own. No moon has been detected, and the physical arrangement makes a stable large satellite unlikely. Rings would face similar difficulties. Material orbiting the planet could be disturbed by the star, heated intensely, or pulled into the planet. The world probably travels alone within its immediate gravitational space, even if KOI-55c exists nearby on the scale of the system. The proposed companion completes one orbit in about 8.23 hours. Its average distance from the star is around 0.0076 astronomical units. The two orbital periods are near a 3-to-2 relationship. While KOI-55c completes about 2 circuits, KOI-55b completes almost 3. This is not an exact resonance in the published values, but it is close enough to suggest that past migration or interaction may have influenced the system. When two bodies repeatedly approach similar positions in their orbits, their small gravitational pulls can accumulate. Depending on the geometry, those interactions can stabilize an arrangement, shift the orbits, or increase orbital eccentricity. The planets are extremely small compared with the star, so each has only a tiny effect on the central object. Their effects on one another could still matter over many thousands or millions of orbits. KOI-55b completes those orbits quickly, allowing repeated interactions to accumulate at a remarkable rate. In one Earth year, there would be more than 1,500 opportunities for the inner planet to complete its circuit. Over 1 million Earth years, it would make more than 1.5 billion orbits. A change too small to notice during one trip could become important after that many repetitions. This is why orbital stability is studied through long numerical simulations rather than by looking at a few circuits and deciding that everything seems fine. Any eccentricity would also affect heating. A perfectly circular orbit keeps the planet at nearly the same distance from the star. An elliptical orbit brings it closer during one part of the year and farther away during another. Because the year lasts less than 6 hours, even these distance changes would repeat several times per Earth day. The planet could experience a rapid heating cycle tied to its orbit, although the already extreme baseline temperature might make the variation seem modest by comparison. Tidal forces tend to circularize very close orbits by removing energy from the motions associated with eccentricity. The same dissipation also affects rotation. KOI-55b may therefore occupy a nearly circular, synchronously rotating state. The planet's past interactions could prevent the arrangement from being perfectly simple. A nearby companion, an uneven mass distribution, or continued tidal evolution could leave small deviations. Astronomers do not have direct measurements precise enough to describe all of those details. The published model also gives the orbit an inclination of about 65 degrees relative to our line of sight. An inclination of 90 degrees would place the orbit edge on from Earth and make transits more likely. At 65 degrees, the planet may pass above or below the visible disk of the star rather than crossing directly in front. That helps explain why the detection method was orbital brightness modulation instead of transit photometry. Kepler may have recorded the changing light of the heated planet without observing a regular planetary shadow. Orbital inclination does not mean the planet itself experiences a steep climb and descent. There is no universal flat surface in space. Inclination describes the orientation of one orbital plane relative to the observer or another chosen reference plane. From KOI-55b's point of view, it simply travels around its star. The angle matters to astronomers because it determines which parts of the orbit we can see and how strongly certain signals appear. The orbit may seem impossible because it violates the layout we learn from our solar system. Planets are expected to remain outside stars, and terrestrial worlds are expected to be separated from stellar surfaces by tens of millions of kilometers. A year is expected to be longer than a working afternoon. Physics does not forbid an orbit lasting 6 hours. Compact stars allow objects to travel much closer without entering the visible surface. Gravity naturally permits short periods when the orbital distance is small. The true difficulty is explaining how a planet arrived there. It could not have remained in the same location while the star expanded into a red giant. It is unlikely to have formed in an ordinary protoplanetary disk at its current distance from the exposed stellar core. Its present orbit must be connected to destruction, migration, or reassembly. This is why the orbit serves as evidence about the past. The distance and period are not merely unusual measurements. They restrict the possible history of the system. A surviving giant planet core could have spiraled inward through the red giant's envelope. A disrupted planet could have left fragments that migrated into nearby orbits. Material expelled during the interaction could have formed a second generation of bodies. Alternatively, the brightness pattern might belong to the star rather than a planet. Each explanation must account for the same short period. If KOI-55b exists, something placed a small body into an orbit that repeats every 5 hours, 45 minutes, and 45 seconds around a stripped stellar core. The current orbit may persist while the star remains a hot subdwarf. Later, the host will exhaust its central helium and continue toward the white dwarf stage. Its luminosity and radius will change, altering the amount of energy reaching the planet. The orbit could expand slightly if the star loses additional mass. A star with less mass exerts a weaker gravitational pull, allowing an existing planet to move outward while conserving angular momentum. The amount of future change depends on how much material the star loses and how quickly. As the host cools into a white dwarf, KOI-55b could eventually receive less heat. The planet might stop glowing as intensely. Mineral vapor could condense. Parts of the surface could become solid. That future would not restore the original planet. Any atmosphere and outer layers lost during the red giant and hot subdwarf phases would remain gone. The surviving object would be a processed remnant orbiting a cooling stellar core. It may also fail to survive long enough to see that stage. Continued evaporation could reduce its mass. Tidal evolution could alter the orbit. The proposed planet may already be smaller than it once was, and may continue changing with every one of its rapid years. A human lifetime of 80 Earth years would contain roughly 122,000 KOI-55b years. The planet's surface would pass through the same orbital geometry more than 100,000 times, while one person grew from infancy to old age. That number makes the orbit sound repetitive, but the planet itself may not return unchanged. A small quantity of material can leave during every circuit. Tides can dissipate a little more energy. The star can complete another set of pulsations. The companion, if present, can apply another weak gravitational pull. An orbit is not a track carved permanently into space. It is a continuing relationship between moving masses. It survives because the relevant forces keep producing nearly the same path. KOI-55b races around its star so quickly that the relationship becomes easier to describe in hours than in days. Its year has been compressed to the length of a long evening. Its rotation may have been forced into the same period, and its star may remain fixed over one scorched hemisphere. Nothing about that arrangement makes the planet physically impossible. What seems impossible is the sequence of events required to create it, and leave it there. A normal planet had to lose its normal orbit. A giant star had to lose most of its body. Some dense object had to avoid complete destruction while moving through the region between them. The 6-hour year is therefore not only a measure of time, it is a measurement of how far the system has changed. It tells us that the planet, if real, did not simply form, cool, and remain where it began. Its orbit records a history of inward movement and severe loss, leading directly to the next question, whether KOI-55b is an ancient survivor, a fragment assembled from destruction, or an object produced after the star had already discarded its former self. KOI-55b's current size, mass and position may all be the results of later destruction. To reconstruct its origin, astronomers have to begin with a planet that may have looked nothing like the scorched body described today. The simplest version of the proposed history starts with a gas giant. Long before KOI-55 became a hot subdwarf, it was a normal star surrounded by a disk of gas and dust. Within that disk, grains collided and stuck together. Larger pieces formed, their gravity attracted more material, and some growing planetary cores became massive enough to collect thick envelopes of hydrogen and helium. This is the standard core accretion picture used to explain many giant planets. A solid core forms first. Once it becomes sufficiently massive, it begins pulling in gas from the surrounding disk. If gas accumulation accelerates before the disk disappears, the result can become a planet similar in broad structure to Jupiter or Saturn. That description should not be taken to mean that KOI-55b has been shown to have formed in precisely this way. We have no direct record of the system's youth. It is a reasonable starting point because the proposed survival model requires an original object much more massive than the small remnant we see today. A gas giant would probably have formed farther from the star than KOI-55b's present orbit. The inner region of a young planetary system is hot, and many of the solid materials useful for constructing a massive core are less abundant there. Farther out, colder conditions allow water and other compounds to freeze, adding more solid material to the disk and helping a core grow quickly. Once formed, a giant planet does not have to remain at its original distance. Planets exchange gravitational energy and angular momentum with the disk around them. These interactions can cause migration, moving a planet inward or outward before the gas disappears. Other planets can also alter one another's orbits. A young system containing several large worlds may experience close encounters, resonances, or scattering. One planet can move inward while another moves outward or escapes completely. The original ancestor of KOI-55b might therefore have formed at a safer distance and later moved closer to the star. It may have spent billions of years in a moderate orbit while the star remained on the main sequence. During that period, the system could have looked far more ordinary. The planet would still have been unlike Earth. A gas giant has no solid surface exposed beneath an atmosphere. Its visible clouds float above deep layers of compressed hydrogen and helium. Pressure increases with depth until the distinction between gas and liquid becomes less useful. Heavy elements are expected to exist inside giant planets, but their arrangement is complicated. Some may be concentrated near the center. Some may be mixed through a broad interior region. Jupiter itself may have a diluted core rather than a small, sharply defined rocky ball. This matters because calling KOI-55b a bare core can create an overly neat picture. The object left after stripping a giant planet would not necessarily resemble an iron sphere removed from a larger shell. It could contain a mixture of rock, metal and other heavy material that had once been spread through the deep interior. The starting planet may also have been larger than Jupiter. A more massive object would have a stronger gravitational grip on its interior and more orbital energy available during the later plunge into the red giant. Both qualities would improve its chances of affecting the star and leaving something behind. A planet with only Earth's present mass would probably not have survived the full journey proposed for KOI-55b. It would contain less material, release less energy while spiralling inward, and have weaker gravity holding its outer layers together. A massive gas giant would enter the crisis with a large reserve of material. It could lose most of its mass and still leave an Earth-sized object. That sounds like a successful outcome only because the word successful is being used very generously. For most of the star's stable life, the planet may have remained largely unchanged. It orbited, absorbed starlight, radiated heat, and interacted gradually with any neighbouring worlds. The serious transformation began when the star exhausted much of the hydrogen in its core. The star expanded into a red giant. Its outer atmosphere moved across the inner planetary system, reaching orbits that had once been empty space. A planet that had spent billions of years outside the star could find itself surrounded by stellar gas. The encounter destroyed the original planetary structure. Hydrogen and helium were heated and removed. The orbit contracted. Pressure, drag, radiation, and tides acted on the interior. By the time the stellar envelope had been expelled, the surviving object may have contained only a small fraction of its former mass. NASA's public description presents KOI-55b as a world that used to be roughly Jupiter-sized before losing its gaseous exterior. That is a useful way to explain the leading proposal, but it is not a directly observed biography. No telescope saw the original giant planet. The idea comes from models designed to explain how a sub-Earth-sized body could appear so close to a post-red giant star. The mass estimate for KOI-55b is around 0.44 Earth masses. Jupiter is about 318 times as massive as Earth. If the original planet had contained roughly 1 Jupiter mass, and the current estimate is correct, considerably less than 1% of the original mass would remain. The exact fraction would depend on the starting mass. A planet several times the mass of Jupiter could lose an even greater percentage. A smaller original world would lose less total material but might struggle to survive. Either way, the transformation would be more severe than removing an atmosphere from Earth. Earth's atmosphere represents only a tiny fraction of our planet's mass. Stripping it away would expose the surface but leave almost the entire world intact. Removing the envelope of a gas giant means taking away most of the planet. Hydrogen and helium are not a thin coating. They form the majority of the object. What remains is not simply the old planet without weather. It is the deepest part of the original body after nearly everything above it has disappeared. The remaining material would respond to the sudden loss of pressure. Deep inside a giant planet, matter is compressed by the weight of enormous overlying layers. Remove those layers, and the interior can expand and rearrange. Materials that were stable under high pressure may transform into different structures. Dense mixtures can separate. Molten regions can circulate. Lighter components can rise and escape, while heavier material sinks. The remnant could continue losing mass even after leaving the red giant's envelope. It would now orbit close to the exposed hot core of the star. Instead of being heated by surrounding stellar gas, it would receive direct radiation from a surface near 27,700 Kelvin. This later erosion could reduce the remnant still further. The object that emerged immediately after the common envelope event may have been larger than the body estimated today. KOI-55b could represent the result of 2 destructive stages: rapid stripping inside the giant star, followed by prolonged evaporation beside the hot subdwarf. The process gives the planet a new appearance, but rebirth should not be understood literally. The original world did not die, and then assemble itself again with all its former parts. A small, dense portion may have remained continuously present while its surroundings changed. It is closer to renovating a building by removing every floor except the basement, moving the basement beside a furnace, and then continuing to sand away the walls. The result is technically connected to the original structure, although the estate agent may prefer not to discuss the details. This single survivor model is not the only proposed explanation. The original discovery paper reported 2 possible small bodies, KOI-55b and KOI-55c. Both have extremely short periods and estimated sizes slightly below Earth's. One possibility is that two separate giant planets entered the red giant. Each could have spiraled inward, lost its envelope, and left a dense core. Multiple giant planets are common enough in planetary systems. Our solar system contains 4. Other stars host several large worlds in a range of orbits. It is therefore possible that KOI-55 began with more than one giant companion. As the star expanded, the innermost giant would be engulfed first. A second planet could enter later as the envelope grew. Their gravitational interactions before and during engulfment might alter the timing and depth of each encounter. 2 planets moving through the envelope would release more orbital energy than one. Together, they might help eject the stellar gas before both cores were destroyed. The surviving remnants could then remain in separate close orbits. This explanation has an obvious difficulty. It requires 2 planets to survive an event that is already difficult for one. Their final orbits are both extremely close, which means both would need to travel deep into the envelope without falling into the stellar core. A second proposal begins with only one massive planet. The planet enters the red giant, loses its gaseous layers, and continues inward as a dense central object. Near the exposed stellar core, tidal forces become strong enough to pull that remnant apart. The largest fragments could remain gravitationally bound as separate bodies. KOI-55b and KOI-55c would then be pieces of one former planetary core. Tidal fragmentation is not an unfamiliar process. Comets can break apart when they pass close to planets or stars. Moons can be disrupted if they move inside the Roche limit of a larger body. Rings may form from material that cannot gather into a stable moon because tidal forces repeatedly pull it apart. A planetary core is much denser and stronger than a comet, so breaking it would require a far more intense gravitational difference across its diameter. The close environment around the stellar core could provide that difference. The side facing the star would be pulled more strongly than the far side. If that tidal stress exceeded the remnant's self-gravity and internal strength, the core could stretch and divide. The immediate result would not be 2 tidy planets travelling calmly in neighbouring circular orbits. There would probably be several fragments, smaller debris, gas and molten material. Their paths could cross, collisions could occur, some pieces might fall into the star, while others escaped or remained nearby. The largest fragments could eventually settle into stable orbits. Their own gravity would draw them into roughly spherical shapes, assuming each contained enough mass. Smaller debris could collide with them or spread into a temporary disk. Interactions with that disk might move the fragments gradually. Gravitational pulls between the fragments could also shift their periods. The proposed periods of KOI-55b and KOI-55c lie near a 3-to-2 relationship, which may be consistent with past migration. The relationship is not exact. That prevents us from presenting the resonance as proof. It is simply one feature that a successful model may try to reproduce. The fragmentation idea has an advantage because it explains why 2 small objects might share a similar composition and history. It also reduces the number of giant planets that must survive engulfment. Its disadvantage is the need to break a dense planetary core into large surviving pieces and then place those pieces into the measured orbits. That process depends on uncertain tidal physics, the strength of the core, the amount of surrounding gas, and the timing of envelope loss. A third broad option removes the requirement that KOI-55b survived the red giant at all. The present body might have formed after the star lost its envelope. When a red giant expels material, not all of it must escape the system immediately. Gas and dust could remain bound, especially if the mass loss is uneven or interacts with a companion. Destroyed planets could add heavy elements to the debris. Some material might settle into a disk around the newly exposed stellar core. Within that disk, particles could collide, gather, and form new bodies. These are sometimes called second-generation planets because they form from material produced during or after the evolution of the original star. A second-generation KOI-55b would not be the surviving core of a gas giant. It would be a new object made from stellar and planetary debris. That sounds like a cleaner escape from the survival problem. The planet would not need to endure travel through the red giant. It would appear only after the envelope had been removed. The new explanation creates different problems. The environment around a newly formed hot subdwarf is extremely hostile to planet formation. Its radiation heats nearby material and can drive gas away. The disk would need to contain enough solid matter to assemble an object approaching Earth's size. The process would also need to happen quickly enough. Dust grains have to collide and stick rather than vaporize, spiral into the star, or be blown out of the system. Building a planet only 0.006 astronomical units from the star is difficult because the temperature is high and the available region is small. Material might first gather farther out and then migrate inward. Fragments created by the disruption of a larger object could also combine rather than beginning from microscopic dust. Second-generation formation therefore includes several possible routes, not one simple recipe. There is another variation in which the red giant destroys a large planet, but leaves a disk of heavy material around the star. KOI-55b could then form from that planetary debris. In this case, the present world would be connected to the original giant without being its continuous surviving core. The distinction may seem rather technical. From a distance, both stories begin with a gas giant and end with a small hot body. The difference concerns whether the same central object survived all the way through. In the first story, the core remains intact while losing its envelope. In the second, the original planet is destroyed, and some of its material gathers again into a new object. That difference affects the expected composition. A direct core remnant might preserve layers or chemical patterns created deep inside the original giant. A reassembled planet would mix debris from different parts of the former planet and possibly from the star's envelope. The present mass and radius could, in principle, help distinguish these cases. A very high density might suggest an iron-rich exposed core. A lower density might indicate a mixture containing silicates or a remaining volatile layer. The available measurements are not precise enough. The mass and radius assigned to KOI-55b were inferred from the brightness model rather than measured through the stronger standard techniques. We do not have a secure density capable of revealing the interior. No atmosphere has been detected. No spectrum of escaping material has shown whether the object is rich in iron, silicon, carbon, or another element. The planet is too distant and too close to its star for current observations to provide that level of detail. The three origin stories therefore remain models rather than confirmed histories. KOI-55b may be the core of one giant planet. It may be a fragment of a larger core that broke apart. It may have assembled from debris after the red giant phase. There is also the least dramatic explanation, which must remain on the table. The planet may not exist. Later analysis of the Kepler data found that the low-frequency signals assigned to KOI-55b and KOI-55c could be combinations of the star's pulsation frequencies. A hot subdwarf vibrates in many modes. When those signals overlap, sums and differences can appear in the measured brightness record. A frequency that repeats every few hours can therefore be produced by stellar behavior without any object completing an orbit. The same light curve can support different interpretations if the signal is faint and the star is complicated. This does not mean the original researchers were careless. Their planetary explanation matched the available data and produced a physically interesting model. Scientific claims are expected to be tested with longer observations, alternative methods, and independent analysis. The later challenge is part of that process. It does not erase the earlier work. It changes how confidently the result should be described. NASA continues to list KOI-55b as a confirmed terrestrial exoplanet, while the NASA Exoplanet Archive also marks the object as controversial. Those labels can coexist because catalogues preserve published classifications, while recording doubts raised by later studies. For the purpose of understanding planetary evolution, the system remains valuable under either outcome. If KOI-55b is real, it may reveal that a planet can lose nearly everything, survive inside a red giant, and remain beside the exposed stellar core. If it is a fragment, it shows that destruction can create a new compact planetary arrangement. If it formed from debris, it supports the possibility of planet formation after a star has left its main sequence. If the signal comes from stellar pulsation, the case demonstrates how an evolved star can imitate a planetary system, and why unusual detections require several forms of evidence. The phrase, "a planet that should not exist," does not mean the laws of physics forbid KOI-55b. It means ordinary planet formation does not place a small rocky world naturally in its present location around its present star. A young rocky planet forming at 0.006 astronomical units would face intense heating even before the star became a red giant. Later expansion would engulf it. A world remaining in the same orbit throughout the star's evolution would almost certainly be destroyed. Something unusual must therefore have happened. The object moved inward after forming elsewhere. It survived as part of a larger planet. It was produced by fragmentation. It assembled after the star changed, or the planetary signal has another source. Each explanation treats the present system as the final result of a long sequence, rather than an original arrangement. The current planet is either a remnant, a fragment, or a second-generation body. That is the practical meaning of rebirth in this system. KOI-55b may have acquired a new size, orbit, composition, and classification after the original planetary system was dismantled. A gas giant can be recognized by its huge hydrogen and helium envelope. Remove that envelope, and the remaining body may be smaller than Earth. It no longer behaves like a gas giant. Its surface can melt and vaporize. Its atmosphere, if one exists, can be made from rock. Astronomers would classify the final body as terrestrial because of its estimated size and composition, even though it may not have formed like an ordinary terrestrial planet. The category describes the object now rather than its entire history. This raises a useful question about identity. Is a stripped giant planet core still the same planet? There is no official point at which an object receives a new personal identity. Astronomy classifies bodies through measurable properties and origin models, not through philosophical paperwork. The orbit remains continuous if the core survives. Some of the original material remains. In that sense, it is the same object. Almost all of its mass and structure may be gone. In that sense, it has become something fundamentally different. A similar problem appears with stars. KOI-55 was once a main sequence star, then a red giant, and is now a hot subdwarf. Astronomers still describe it as the same star, even though its radius, surface temperature, fuel, and outer layers have changed dramatically. The planet may have followed a parallel transformation. The star lost its envelope and exposed its helium-burning core. The planet lost its envelope and may have exposed a dense heavy element core. Both objects were reduced. Both became hotter at their visible boundaries. Both ended in a tight system that could not have existed in the same form during their youth. The difference is that the star's present condition is well established, while the planet's is not. Spectroscopy and astroseismology reveal the host's temperature, gravity, pulsations, and evolutionary state. KOI-55b appears only through a faint repeated pattern in the star's brightness. The proposed transformation is therefore built backward from a small amount of information. Astronomers know the current stellar structure. They identify two low-frequency signals. They calculate the orbital periods those signals would represent. They estimate the size and temperature of the bodies needed to produce them. After that, they ask what history could place such bodies there. The gas giant core model is an answer to that question, not an event witnessed directly. This difference between measurement and reconstruction is essential. The orbital periods come from the repeating frequencies under the planetary interpretation. The temperatures and sizes come from models. The original gas giants, common envelope journey, fragmentation, and second-generation formation are proposed explanations. A good model must connect all of those pieces without violating known physics. It should explain the star's missing envelope, the tiny orbital distances, the possible presence of two bodies, and their survival under extreme radiation. It should also make predictions that could be tested. A stripped core may have a particular density. Escaping vapor may contain heavy elements. A fragment system may show a specific orbital relationship. A pulsation explanation should reproduce the observed frequencies from the star's known modes. The planet's origin cannot be settled merely by making the survival story more detailed. A detailed story can still describe an object that is not there. The existence of the body must be established independently before its past can be reconstructed with confidence. That requirement leads us away from the red giant, the lost gas envelope, and the possible exposed core. We have to return to the measurements themselves. The planet was proposed only after astronomers measured the brightness of the combined system for a long time, and noticed two faint patterns repeating beneath the much stronger activity of the star. The spacecraft responsible was NASA's Kepler Space Telescope. It launched in March 2009 and spent the main part of its mission watching a fixed region of the sky containing parts of the constellations Cygnus and Lyra. Rather than moving constantly from one target to another, Kepler stared at the same field and measured the brightness of more than 100,000 stars again and again. That approach was deliberately repetitive. A single measurement can reveal how bright a star appears at one moment. Thousands of measurements collected over weeks, months, or years can show whether that brightness changes on a regular schedule. Kepler's main purpose was to find planets using the transit method. A transit occurs when a planet passes between its star and the telescope. The planet blocks a small portion of the starlight, producing a temporary decrease in brightness. If the decrease returns at regular intervals, it may reveal the planet's orbital period. The depth of the dip can help estimate the planet's size relative to the star. A large planet blocks more light than a small one, assuming both cross similar parts of the stellar disk. This sounds simple when drawn as a planet passing in front of a circle. The actual measurement is much more difficult. A planet the size of Earth crossing a sun-sized star blocks only a very small fraction of the light. The telescope must remain stable, the detector must be sensitive, and the same pattern must usually repeat several times before astronomers can treat it seriously. Stars create additional complications. They have dark spots, bright regions, flares, convection, rotation, and pulsation. Their brightness is not always constant. Spacecraft also produce instrumental changes as temperatures vary, pointing shifts, detectors age, and electronic systems behave in ways that are rarely included in the cheerful diagrams. Kepler was designed to deal with tiny variations. Its main instrument was a photometer, a device that measures light rather than producing ordinary photographs for display. The telescope focused starlight onto a large array of electronic detectors. Each target appeared across a small collection of pixels, and the amount of recorded light in those pixels was measured repeatedly. The result for each star was a long sequence of numbers. One number represented the measured brightness at one time. The next represented it a short time later. Plotted on a graph, those values formed a light curve. Time appeared along the horizontal direction, while brightness appeared vertically. A perfectly constant star measured by a perfectly constant instrument would produce a flat line. Neither stars nor instruments are that cooperative, so real light curves contain slopes, bumps, dips, waves, interruptions, and noise. For most Kepler planets, astronomers searched those curves for repeated transit-shaped dips. KOI-55 was being studied for another reason. It was already known to be a pulsating hot subdwarf, and its vibrations offered a way to investigate its interior. The star does not pulse like a single balloon, expanding and contracting at one steady rate. Many patterns can move through it at the same time. One region may move outward while another moves inward. Some waves travel mainly through outer layers, while others respond to conditions deeper inside. These motions slightly change the star's radius, temperature, and visible brightness. Kepler recorded the result as a complicated collection of repeating variations. Astronomers can use those variations to study the internal structure of the star. The method is called astroseismology. It resembles seismology on Earth, where researchers use waves from earthquakes to learn about layers beneath the surface. An earthquake wave changes speed or direction as it passes through different materials. By measuring when waves arrive and how they behave, geologists can infer the structure of Earth's crust, mantle, and core. A star does not provide instruments placed at different points on its surface, but its changing light contains information about the waves moving through it. Each pulsation frequency responds to the star's mass, density, chemical layering, rotation, and evolutionary condition. KOI-55 was particularly useful because it showed both pressure modes and gravity modes. Pressure modes are driven mainly by pressure acting as a restoring force. They usually have shorter periods and are especially useful for studying parts of the star closer to the surface. Gravity modes are controlled mainly by buoyancy. They generally have longer periods and can probe deeper layers. The word gravity here refers to the restoring effect that moves displaced material back toward its original position, not to the planet's orbit. A star showing both types is called a hybrid pulsator. Its light curve contains many frequencies, each one representing a different mode or interaction. Listening to these pulses does not involve sound in space. Sound requires a material such as air, water, or stellar gas to carry pressure waves. Kepler detected changes in light after the internal waves reached or affected the star's visible layers. The word listening is still useful because the analysis has something in common with separating musical notes. A chord can contain several tones at once. A trained listener may distinguish some of them directly, while software can separate the frequencies more precisely. Astronomers perform a similar separation using a mathematical technique called a Fourier transform. The name may sound severe for a bedtime journey, but the basic idea is manageable. A complex signal can often be represented as a collection of simpler waves. Each simple wave has a frequency, an amplitude, and a phase. The frequency tells us how often it repeats. The amplitude describes the strength of its contribution. The phase tells us where it is within its cycle at a particular time. A Fourier transform takes the light curve and shows how much power or amplitude appears at different frequencies. Instead of looking only at brightness versus time, astronomers can examine a frequency spectrum filled with peaks. A strong, regular pulsation creates a clear peak at its frequency. A weaker pulsation creates a smaller one. If the star has many modes, the spectrum can look like a line of narrow spikes with clusters in different regions. Frequency is measured in hertz, meaning cycles per second. Stellar pulsations and planetary orbits are often much slower than 1 cycle per second, so astronomers use microhertz. 1 microhertz is 1/1,000,000th of a cycle per second. The period and frequency describe the same repetition from opposite directions. A high frequency means a short period, a low frequency means a long one. A signal repeating every 6 hours has a frequency of roughly 46 microhertz. It completes far less than 1 cycle per second, but it repeats often enough to produce a narrow peak when many days of data are combined. The strong pulsations of KOI-55 appeared across the Fourier spectrum. Researchers identified dozens of stellar modes and used them to build a model of the star. That model helped determine its mass, radius, surface gravity, and internal structure. After accounting for the known pulsations, 2 weaker signals remained at much lower frequencies. One corresponded to a period of approximately 5.76 hours. The other corresponded to about 8.23 hours. The first became associated with KOI-55b. The second became associated with KOI-55c. These signals were extremely faint. Their amplitudes were measured in parts per million. A variation of 50 parts per million means that the total brightness changes by about 50 units out of every million. That is equivalent to 0.005 of 1%. The change is real only if the data and analysis can distinguish it reliably from noise, instrumental effects, and the star's many other variations. A human eye could not notice the difference by looking at the star. Even if KOI-55 were bright enough to see without a telescope, which it is not, the change would be much too small. Kepler could detect variations at this level because it collected light continuously and repeated its measurements over long periods. A faint periodic signal becomes easier to identify when the same cycle occurs hundreds or thousands of times. Random noise changes unpredictably. When many measurements are combined, some random variations partly cancel. A stable repeating signal continues to add at the same frequency. The short proposed orbital periods helped in that respect. A planet requiring several years to complete an orbit might repeat only once or twice during a mission. KOI-55b would repeat more than 4 times per Earth day. In 100 days, the 5.76-hour signal completes more than 400 cycles. Astronomers could combine information from all of them, increasing the chance of finding a weak pattern. The 2 signals did not look like ordinary transits. There were no clear, sharp dips showing a body crossing the face of the star. The orbital orientation was estimated to be around 65 degrees to our line of sight, which could allow the planets to pass above or below the visible stellar disk. Instead, the researchers interpreted the signals as orbital brightness modulation. This means the total light from the system changed gradually as each proposed planet moved around the star. The same general effect can be observed with the Moon. A full moon appears brighter than a crescent because more of its illuminated hemisphere faces Earth. The Moon is not producing most of that visible light itself, it is reflecting sunlight. A close exoplanet can create a similar phase curve. When its bright day side faces the telescope, the system becomes slightly brighter. When the dark side faces us, the system becomes slightly dimmer. KOI-55b would add another source of light because it is intensely heated. At thousands of degrees, the planet would emit substantial thermal radiation. Its surface would glow rather than merely reflect the star. As the planet orbited, the amount of that glowing hemisphere visible from Earth would change. The system's brightness could rise and fall smoothly once during every orbit. If the planet passed behind the star, its contribution would disappear temporarily. This is called a secondary eclipse or occultation. The star would block the planet rather than the planet blocking the star. A complete phase curve can contain reflected light, thermal emission, eclipses, and changes caused by the shape or motion of the star. In many close systems, astronomers also consider Doppler beaming and ellipsoidal variation. Doppler beaming occurs because the star's motion toward and away from us slightly alters the observed brightness. Ellipsoidal variation occurs when the gravity of a close companion stretches the star, causing the visible area to change through the orbit. KOI-55b is too low in mass to produce a large stellar deformation or a strong gravitational wobble. The original interpretation therefore focused mainly on light from the heated planet. The researchers estimated how much radiation reached an object at the proposed orbital distance. They calculated how hot the illuminated side could become and how much light a body of a given size might emit. They then compared the predicted modulation with the measured amplitude. A larger planet has more glowing surface area and contributes more light. A smaller planet contributes less. This is how the proposed radius was estimated. It did not come from the depth of a transit. It came from a brightness model involving the planet's temperature, size, reflectivity, heat distribution, and orbital inclination. The mass was also not measured directly through a large stellar wobble. It was inferred from assumptions about the likely composition and internal structure of the planet. That makes the published radius and mass less direct than values obtained for some other exoplanets. They are consequences of the planetary model. If the brightness signal has a different source, those planetary properties no longer follow. The two periods offered another reason for interest. Their relationship was close to 3:2. While the inner proposed planet completed roughly 3 orbits, the outer one completed about 2. Planetary systems frequently contain period ratios near small whole numbers. Gravitational interactions and migration through gas or debris can guide planets toward these arrangements. The near resonance did not prove that the signals were planets, but it made the interpretation more appealing. 2 unrelated signals happening to resemble neighbouring orbital periods seemed less likely than 2 bodies shaped by the same system history. The physical story also appeared to fit. The star was an exposed post-red giant core. Any close planets should have been engulfed. If the signals represented small hot bodies, they could be remnants of larger planets that had survived the envelope. The detection and the survival model supported one another. The light curve suggested 2 short periods. The periods suggested close orbits. The close orbits required an unusual evolutionary history. That history could also help explain why the star had lost its envelope. A coherent explanation had formed from very small variations in light. Before publishing such a result, astronomers had to consider alternatives. One possibility was contamination from another star. Kepler's pixels covered a relatively large area of sky compared with the apparent separation between many stars. Light from a nearby variable star could enter the same measurement aperture. A repeating signal might then be assigned to the wrong target. Researchers examine images, catalogue nearby objects, and measure whether the centre of light shifts during a variation. If the signal originates from a neighbour, the distribution of brightness across the detector may move slightly. Instrumental effects also require attention. Kepler's pointing could drift. The spacecraft adjusted its orientation. Temperature changes affected the detector. Energetic particles struck the electronics. Data gaps appeared when observations were interrupted. A processing pipeline corrected many of those effects. Raw measurements were calibrated, faulty values were identified, long-term trends were removed, and the light curve was prepared for analysis. Every correction involves choices. Removing too little can leave instrumental patterns in the data. Removing too much can weaken or distort a real astronomical signal. This is especially important at low frequencies, where slow spacecraft changes and long stellar variations overlap. A signal repeating over hours occupies a different region from a transit lasting minutes, but it can still be affected by how the data are detrended. The star's pulsations were the most serious complication. KOI-55 contained many genuine frequencies. Some had large amplitudes, others were faint enough to sit close to the noise level. The original team argued that the 2 low-frequency signals could not be explained by the known strong pulsation modes. Standard gravity mode pulsations in a hot subdwarf were not expected below a certain frequency range. The 2 signals sat beneath that approximate cutoff. That made an orbital origin plausible. A planet can move with almost any period allowed by a stable orbit. It does not care whether the corresponding frequency lies outside the normal pulsation range of the star. The signal also appeared coherent enough to be treated as a repeating orbital variation. An orbit should maintain a stable period unless something exerts a significant disturbance. Stellar pulsations can drift in phase, change amplitude, or interact. The distinction is useful in principle. A planet behaves like a clock. Each orbit returns after nearly the same interval. A pulsation mode may also behave like a clock, but multiple modes can interfere in complicated ways. 2 nearby pulsation frequencies can produce beating. Imagine 2 tones with almost but not quite the same frequency. At some moments they reinforce each other, producing a larger combined amplitude. At others they partially cancel. The rise and fall of that combined signal occurs at the difference between the frequencies. A pair of higher frequency stellar pulsations can therefore create a much slower pattern. This low frequency beat does not require the star to possess a true pulsation mode at the slower frequency. It emerges from the interaction of the faster variations. Frequency combinations can involve sums as well as differences. If a star has many modes, there may be numerous possible combinations. Weak modes that were initially overlooked can create low-frequency features in the Fourier spectrum. That possibility became central when other researchers revisited the KOI-55 data. They examined both short cadence and long cadence Kepler observations, tested different reduction methods, and compared the measured signals with simulations. Kepler's long cadence observations combined measurements into intervals of about 29.4 minutes. Short cadence sampled much more frequently, close to once per minute. The shorter sampling was useful for resolving rapid stellar pulsations, while the longer record provided extensive coverage. A true planetary modulation should preserve a highly stable frequency over time. Its amplitude might change slightly because of measurement noise or evolving surface conditions, but the orbital clock should remain narrow and consistent. The later analysis divided the KOI-55 observations into separate time intervals and examined whether low-frequency peaks appeared. The researchers also simulated weak planetary signals with constant frequencies and placed them into artificial light curves containing realistic sampling and noise. The simulated orbital signals remained within a narrow frequency range. The proposed KOI-55 signals varied more than expected from a constant orbital source. The change was particularly noticeable for the signal assigned to the outer planet. Its frequency shifted by an amount larger than the simulations allowed for a stable sinusoidal planet signal. The researchers then searched for combinations of the star's lower amplitude pulsation modes. They found that beating between those modes could produce signals close to the frequencies attributed to KOI-55b and KOI-55c. Their conclusion was that the two low-frequency signals were likely products of the star's pulsations rather than orbiting planets. This conclusion did not show that the original peaks were invented or that the telescope had failed. The peaks were present in the analysis. The disagreement concerned their source. The same repeated change in brightness could be described as the changing glow of a planet or as interference between stellar oscillations. Deciding between those explanations requires more than locating a peak on a graph. Astronomers ask whether the frequency remains stable, whether the amplitude changes, whether related harmonics appear, whether the signal survives different processing methods, and whether an independent detection method confirms it. A transit would help greatly. So would a measurable gravitational pull on the star. A spectrum of escaping planetary material could provide separate evidence. None of those confirmations has been secured for KOI-55b. The host star is faint, which makes precise spectroscopic follow-up difficult. The proposed planet has less than half Earth's mass, so the gravitational effect on the star would be extremely small. The star's own pulsations would complicate the measurement further. Direct imaging is not realistic with current instruments. The planet is separated from its star by only a tiny angle, as seen from thousands of light-years away. Even if a telescope could resolve that angle, the star would outshine the planet. The detection therefore remains tied closely to the Kepler light curve. That is why the interpretation of those small frequencies matters so much. NASA's Exoplanet Archive continues to list KOI-55b and KOI-55c as confirmed planets based on the 2011 publication. It also marks them as controversial because of the later reanalysis. This may look inconsistent, but scientific catalogues often preserve the history of a claim. A published object can remain in the confirmed table, while notes warn users that its status has been challenged. The archive is not declaring that both conclusions are equally certain. It is recording the original classification and the later dispute. The method listed for KOI-55b is orbital brightness modulation. That phrase contains the entire chain of reasoning. A brightness pattern was measured. It was assigned an orbital period. A very hot body was modelled as the source. Unlike a clear transit, the signal does not show the shape of the planet passing over the star. Unlike radial velocity, it does not directly reveal the star responding to the planet's gravity. It relies on the idea that the planet contributes a faint changing glow. If the star can create the same change internally, the identification becomes uncertain. That does not make orbital brightness modulation an invalid method. Phase curves have been used successfully to study many close planets. They can reveal dayside temperatures, heat circulation, atmospheric properties, reflected light, and orbital geometry. The method is strongest when combined with other evidence. A planet may first be found through transits, then studied through its phase curve. In that situation, the existence and period of the planet are already known. For KOI-55b, the phase-like modulation carried most of the detection by itself. The interpretation, therefore, had to support more weight. The story shows how exoplanet discovery often differs from the image suggested by the word found. Astronomers rarely look through a telescope and immediately see a new world. They measure light, motion, timing, or gravitational lensing. They build models and compare possible causes. A discovery can begin as a repeated absence of light during a transit, a shift in a star's spectral lines, or a tiny pulse buried in a Fourier spectrum. The planet is the explanation that best connects the measurements. Sometimes the explanation becomes stronger when new instruments confirm it. At other times, a different explanation begins fitting the data better. KOI-55b sits between those outcomes. Its proposed signal was subtle enough to reveal the power of Kepler, but complicated enough to reveal the limits of interpretation. The telescope measured changes of only a few dozen parts per million in the light of a pulsating star thousands of light years away. Researchers converted two frequencies into periods, the periods into orbits, the signal amplitudes into planetary sizes, and the system into a history involving engulfed gas giants and exposed cores. The question now is not whether Kepler detected a repeating signal. It did. The harder question is whether that signal was produced by a planet. Those statements may sound almost identical, but in astronomy they can lead to very different conclusions. A telescope records light. It does not record labels explaining what caused each change. Astronomers examine the pattern, compare possible sources, and decide which explanation fits best. Sometimes one interpretation becomes so strongly supported that there is little practical doubt. In other cases, several explanations remain possible. KOI-55b belongs to the second group. NASA's public exoplanet catalogue currently presents KOI-55b as a terrestrial planet discovered in 2011. The NASA Exoplanet Archive also places it in the confirmed planet category. On the same page, however, the archive marks it as controversial and links that warning to the later study arguing that the signal may be stellar rather than planetary. This creates an unusual combination of labels. Confirmed and controversial appear together. It can look as though the catalogue has answered yes and no at the same time, which is not normally the most helpful response to a straightforward question. The reason is that scientific catalogues preserve the history of published discoveries. KOI-55b entered the archive after the original research passed peer review and presented a planetary interpretation. A later study challenged that interpretation, but the challenge did not automatically remove the object from every existing list. Different catalogues also use different rules for changing an object's status. Some remove disputed planets quickly, others retain the original classification and add a note. A catalogue is a working record, not a final declaration delivered after the universe has finished submitting evidence. To decide how strongly we should believe in KOI-55b, we need to separate the parts of the case that are directly measured from the parts that depend on interpretation. The star exists. Its light has been observed and analysed extensively. It is a compact, hot, pulsating subdwarf with roughly half the mass of the Sun and about 1/5 of its radius. Its brightness changes at many measurable frequencies. 2 additional weak signals were found in the low-frequency region of its data. One repeated on a timescale of about 5.76 hours. The other repeated on a timescale of about 8.23 hours. Those signals exist in the processed measurements. The debate concerns what made them. Under the planetary explanation, the 5.76-hour signal comes from KOI-55b. The planet is strongly heated by the star, so its illuminated side glows. As it moves through its orbit, different amounts of that bright side face Earth. The combined light from the star and planet therefore rises and falls slightly. The 8.2 3-hour signal is assigned to KOI-55c, a second proposed body orbiting a little farther out. The periods lie near a simple relationship, adding to the impression that the two signals belong to a compact planetary system. The original explanation has several attractive features. The signals repeat. Their periods are physically possible for objects orbiting a compact star. Their amplitudes can be matched by very hot bodies somewhat smaller than Earth. Their close orbits can be connected to the earlier red giant phase of the host. The history also offers a possible explanation for the host star itself. Giant planets spiraling through its expanded envelope could have released energy and helped remove that envelope, leaving the hot subdwarf behind. The planets would then survive as stripped cores. This is a coherent model. The proposed planets explain the signals, the red giant explains their unusual condition, and the inward spiral helps explain the star's missing outer layers. A coherent model is valuable, but it is not automatically correct. Several incorrect explanations can arrange known facts into a convincing sequence. The important test is whether the model predicts observations that competing explanations cannot reproduce. The planetary case lacks some of the usual independent evidence. KOI-55b does not produce a clearly detected transit. Astronomers do not see it passing across the face of the star and blocking a measured amount of light. There is also no secure radial velocity detection. A planet's gravity pulls on its star, causing the star to move slightly toward and away from Earth during the orbit. That motion can shift the wavelengths in the stellar spectrum. KOI-55b's proposed mass is less than half that of Earth. Its host is distant and faint, while the stellar spectrum is affected by pulsations. The expected gravitational signal would be extremely difficult to measure. No separate image shows the planet. The apparent distance between the planet and star is much too small for current telescopes to resolve at the system's distance. The star would also be vastly brighter. No confirmed spectrum has revealed an atmosphere or a trail of material escaping from KOI-55b. Such a detection could provide strong, independent support, but obtaining it would be a major observational challenge. The planet's existence therefore rests mainly on the interpretation of the brightness modulation. That places considerable weight on two weak peaks within the frequency spectrum of a complicated pulsating star. The later challenge focused directly on that weakness. KOI-55 produces numerous pulsation modes. Each mode contributes a periodic variation to the light curve. Some are strong and easy to identify. Others have low amplitudes and can be difficult to distinguish from noise. When multiple pulsations are present, they do not always appear as completely independent signals. Their frequencies can interact mathematically and physically. Sums, differences, and harmonics may appear in the Fourier spectrum. Suppose one stellar pulsation repeats at one frequency and another repeats at a slightly different frequency. When the two waves reinforce each other, the combined brightness variation becomes larger. When they oppose each other, the variation becomes smaller. This produces a slower pattern known as beating. The beat frequency is related to the difference between the two original frequencies. Two rapid stellar oscillations can therefore create a long period variation without any planet being present. The effect is familiar in sound. Two musical notes that are almost, but not exactly, the same pitch can produce a repeating rise and fall in volume. No third low note is being played. The slow pulse appears because of interference between the two higher notes. A pulsating star can create a similar result in light. If KOI-55 has enough weak modes, combinations between them may generate signals near the proposed planetary periods. The 2019 reanalysis examined this possibility using a longer set of Kepler observations and several data processing approaches. The researchers studied both short cadence and long cadence measurements, separated the observations into time intervals, and compared the real signals with simulated planetary signals. A planet following a stable orbit should maintain a very consistent frequency. Its brightness contribution may vary slightly if the surface changes, but the period should not wander significantly over the limited duration of the Kepler data. The researchers added artificial signals with constant frequencies to simulated light curves and measured how much those frequencies appeared to move because of noise and sampling. The artificial planetary signals remained within a narrow range. The low-frequency features in the real KOI-55 data changed more than those simulations predicted. The signal associated with the proposed outer planet showed particularly noticeable variation. The researchers also identified combinations of lower amplitude stellar pulsations that could account for the disputed frequencies. Their conclusion was that the signals were likely produced by the star's oscillations rather than by orbiting planets. That conclusion is significant because it explains the same measurements without requiring two extraordinary surviving worlds. It uses processes already known to occur within the observed star. When two explanations fit the data, scientists often favour the one requiring fewer unsupported assumptions. The stellar explanation begins with a star known to pulsate in many modes and shows how those modes can create the observed frequencies. The planetary explanation requires two small bodies in extremely close orbits, each heated to enormous temperatures, each surviving or forming after a red giant event, and each producing just enough changing light to match the weak signals. This does not prove that the simpler explanation is correct. Nature is under no obligation to avoid unusual arrangements. Planets do survive around stellar remnants, and systems discovered elsewhere have repeatedly demonstrated that unusual does not mean impossible. The difference concerns evidence. Extraordinary systems require observations strong enough to separate them from ordinary sources of error or stellar variability. The original team did not simply find two random bumps and immediately announce planets. The signals were periodic, appeared below the expected range of ordinary gravity mode pulsations, and produced a plausible planetary model. The suggested period relationship added further interest. The later study benefited from more extensive data and a focused investigation of combination frequencies. Its authors argued that the apparent stability and interpretation of the signals changed when the complete observations and alternative reductions were considered. The disagreement is therefore not between careful science and careless science. It is between two analyses of a difficult dataset. Scientific uncertainty is sometimes presented as a weakness, especially when the public expects every object to be either real or false. In practice, uncertainty is a necessary part of measuring anything close to an instrument's limits. Kepler was capable of detecting extremely small brightness changes. That sensitivity allowed it to find thousands of planets, including many that could not have been discovered through earlier methods. Greater sensitivity also reveals more stellar behaviour and more instrumental complexity. The telescope detects planets, but it also detects star spots, pulsations, binary interactions, background stars, detector noise, and patterns produced during data processing. A weak signal must be examined against all of those possibilities. The challenge becomes harder around an evolved pulsating star because the host itself produces a dense collection of frequencies. KOI-55b has another disadvantage. Its proposed detection method is unusual. Many confirmed planets produce recurring transits with a recognizable shape. Others create a measurable radial velocity signal. Some are detected through gravitational microlensing, direct imaging, or precise timing variations. Orbital brightness modulation is a legitimate source of information, but it is usually most convincing after a planet has been identified independently. Once a transiting planet's period is known, astronomers can search for a matching phase curve and use it to measure temperature or atmospheric circulation. For KOI-55b, the modulation served as the primary evidence for the planet itself. There was no strong transit to establish the period first. This creates a circular risk. The signal is interpreted as light from a heated planet. The size and temperature of the planet are then calculated from the signal. Those calculated properties are later used to explain why the signal should exist. The reasoning is not invalid if the initial planetary interpretation is supported independently. Without that support, the model can become too dependent on its starting assumption. The same concern applies to the planet's proposed past. The gas giant survival story is physically interesting and may be possible. It cannot confirm KOI-55b because it was created to explain the object after the signal was identified. A plausible origin does not prove an object exists. Astronomers can develop a completely realistic model of how an undetected planet might form. The model shows that the planet could exist, not that it does. Confirmation would require new evidence that behaves differently under the planetary and stellar explanations. One possibility would be a stable phase signal detected again with an independent telescope over a much longer period. If the 5.76-hour frequency remained fixed, while the surrounding pulsation modes changed that would support an orbital clock. The observation would need enough precision to separate the weak modulation from stellar oscillations. It would also need careful handling of instrumental effects so that a processing method did not create or suppress the signal. Measurements at several wavelengths could help. Thermal radiation from a hot planet changes with wavelength in a predictable way. Stellar pulsation amplitudes also vary with wavelength, but not necessarily in the same pattern. If the signal were stronger at wavelengths, where the proposed planet should emit more light, that would support the planetary interpretation. A stellar combination frequency might show a different color dependence. A secondary eclipse would be particularly useful. If the planet passes behind the star during each orbit, the system should lose the planet's light at a precise phase. The eclipse shape and timing would provide information separate from a smooth pulsation. The published geometry may prevent an eclipse from occurring from our viewpoint. The absence of one therefore does not disprove the planet, but detecting one would greatly strengthen the case. Spectroscopy of escaping material would offer another route. A body heated to thousands of degrees may release atoms and ions from its surface. If absorption or emission lines moved with the proposed orbital period, they could reveal material physically connected to a planet. The signal would be extremely difficult to measure because the system is distant and the planet is small. The host's ultraviolet radiation would also alter the escaping gas. Difficult is not the same as impossible, but no such confirmation is currently available. Planetary gravity could theoretically be detected through precise changes in the star's motion. For a proposed mass of 0.44 Earths, the effect would be tiny. Stellar pulsations would probably exceed it by a large margin. Timing the star's pulsations offers a different possibility. A planet makes the star orbit the shared center of mass, slightly changing the distance that starlight travels to Earth. Stable stellar pulses could then arrive a little early or late during the planetary orbit. This method has detected companions around some pulsating stars. KOI-55b's low mass, an extremely short period make the expected timing shift very small, and the complex pulsations may prevent a useful measurement. A nearby companion might also perturb the orbit. If KOI-55b and c are real, their gravitational interaction could cause predictable changes in phase or period. Detecting those changes could provide evidence that two bodies are exchanging gravitational influence. The proposed masses are small, and the signals themselves are uncertain, so identifying such interactions would be challenging. Still, a dynamical pattern would be harder for unrelated stellar frequencies to imitate. Until an observation like these resolves the issue, the most accurate description is cautious. KOI-55b remains listed as a confirmed planet in major NASA resources, but its existence is disputed by a peer-reviewed reanalysis that provides a plausible stellar explanation for the detection signal. Calling it definitely real goes beyond the evidence. Calling it definitely non-existent also goes beyond the available evidence. The balance has shifted toward greater doubt since the original announcement. but the catalogue has not closed the case. Some astronomers would refer to it as a controversial planet. Others might prefer planet candidate or putative planet. The choice reflects how much weight they give to the original detection and the later challenge. For a general audience, the phrase possible planet is the safest. It preserves the reason the object remains scientifically interesting without presenting model-dependent properties as direct observations. The temperature of 6,800 degrees Celsius is not independently measured. It follows from the planetary interpretation. The mass, radius, atmosphere, surface, and evaporation history also depend on that interpretation. If the signal belongs to stellar pulsation, there is no planet whose surface is hotter than the Sun. There is only a hot subdwarf producing a complicated pattern of light. That alternative is not disappointing. A star creating frequencies that closely imitate two planets is an important result. It warns astronomers that pulsating stellar remnants can produce false planetary signals. Future searches around hot subdwarfs, white dwarfs, and other evolved stars benefit from that warning. Researchers can test frequency stability, examine combinations of weak modes, compare reduction methods, and demand independent evidence before assigning a planetary cause. The disputed detection has therefore contributed to astronomy, whether or not KOI-55b exists. If the planet is real, it expands our understanding of survival. A dense planetary core may endure engulfment, tidal stress, and extreme irradiation. Giant planets may play a role in removing red giant envelopes. Small bodies may occupy orbits lasting only a few hours around exposed stellar cores. If the planet is not real, the system expands our understanding of stellar pulsation and observational caution. Weak frequencies can combine in misleading ways. A coherent physical story can grow around a signal before its origin has been fully established. Both outcomes are useful because science is not only a collection of confirmed objects, it is also a method for deciding how much confidence an observation deserves. KOI-55b sits near the boundary between a discovery and an interpretation. It has a name, catalogue entry, estimated mass, radius, temperature, and orbital period. Those details make it feel established. Behind them remains a faint signal and an unresolved argument about its cause. The planet may be racing around the star while its surface vaporizes. It may be the final core of a former gas giant that passed through a red giant's envelope. It may have completed several orbits while you listen to this section. It may also be absent, with every proposed orbit produced by waves moving through the star itself. The scientifically responsible answer is therefore not a dramatic yes or no. It is that KOI-55b has not reached the level of certainty suggested by its detailed public description. It remains a serious but disputed interpretation of Kepler data. That uncertainty does not require us to erase the journey we have taken. Every part of it has shown what the measurements would imply if the planetary model is correct. We have also seen why astronomers must test that model against alternatives. We began with a small object described as hotter than the visible surface of the Sun. That description gave us a clear destination, but the journey revealed something less simple. KOI-55b is not a world that astronomers have photographed or visited. It is a possible explanation for two very faint patterns in the light of an evolved star. Even so, following that explanation has taken us through a large part of modern astronomy. We have considered how stars age, how planets form, how gravity changes orbits, how radiation removes atmospheres, and how a telescope can detect variations too small for human eyes to notice. The system lies thousands of light years away in the direction of Cygnus, the light reaching us left long before anyone knew that stars were distant suns. It travelled through interstellar space until part of it entered the Kepler telescope and landed on an electronic detector. Kepler did not know it was watching anything unusual. It measured brightness at one moment and then measured it again. It repeated that task with extraordinary patience. From those measurements, astronomers studied the host star's pulsations. The star turned out to be a compact hot subdwarf, an exposed core left after a red giant lost most of its outer material. That fact alone gives the system an unusual history. The star was once larger and cooler at its visible surface. It exhausted hydrogen in its centre, expanded, and spread its atmosphere across a large region. Most of that atmosphere later escaped. The exposed remnant contracted until it became much smaller than the Sun, while its visible surface became far hotter. It now contains roughly half the Sun's mass, within a body only about 1/5 as wide. Helium fusion continues in its centre. Its surface releases intense blue-white and ultraviolet radiation. Around that star, the original study proposed 2 small planets. The inner one became KOI-55b. According to the model, it travels less than 1 million kilometres from the star's centre. One orbit takes just under 6 hours. The planet may complete more than 4 years during one Earth day. The star could appear more than 30 times wider than the Sun appears from Earth. One side of the planet may face it continuously, because tidal forces have probably synchronized the planet's rotation with its orbit. There would be no ordinary sunrise on the illuminated hemisphere, and no ordinary sunset. The star would remain in approximately the same part of the sky, while the planet raced around it at hundreds of kilometers per second. The estimated temperature reaches roughly 6,800 degrees Celsius. That is higher than the temperature of the Sun's photosphere, the bright layer visible from Earth. It is not higher than the Sun's core or corona, and it does not make the planet a star. KO. ESO's 55b would receive its heat from the nearby host, rather than producing it through sustained nuclear fusion. At that temperature, a familiar rocky surface would not remain stable. Silicate material and metals could melt, boil, and enter the atmosphere. Ultraviolet radiation could break molecules apart and remove electrons from atoms. The atmosphere, assuming one exists, might consist largely of planetary material released from below. Sodium, iron, magnesium, silicon, and oxygen could move through a hot mixture of vapour and plasma. Some gas might flow toward the night side, cool and condense. Other material might escape the planet completely. The surface would then be connected continuously to the atmosphere and to the surrounding space. These conditions were not measured directly. They are consequences of applying physics to the proposed size, orbit, and stellar environment. The same is true of the planet's history. If KOI-55b is real, it probably did not begin as the small rocky object described today. It may once have been a gas giant. Hydrogen and helium could have surrounded a dense interior containing hundreds of times more material than the present remnant. When the star expanded into a red giant, that planet may have entered the stellar atmosphere. Gas drag would have reduced its orbital energy and drawn it inward. The surrounding stellar material would have stripped away the planetary envelope. Heat, pressure, shock waves, and tidal forces would have changed every part of the world. The planet's movement may have transferred energy into the red giant's atmosphere. That energy could have helped push stellar gas away, contributing to the formation of the hot subdwarf. Under this interpretation, the planet and star transformed each other. The star removed nearly all of the planet, while the planet helped remove nearly all of the star's envelope. A dense core may have remained. It would have left the red giant phase in a tight orbit around the newly exposed stellar remnant. Another possibility is that one large core broke into fragments. KOI-55b and its proposed companion could be separate pieces of the same former planet. Material released during the destruction might have formed a temporary disk. Gravitational interaction and migration could have shifted the fragments into nearby orbits. There is also the possibility of second-generation formation. A new body might have assembled from debris after the red giant had already lost its envelope. Each explanation attempts to solve the same problem. An ordinary small planet should not be sitting in that orbit after the star's expansion. Something must have moved, survived, broken apart, formed again, or been misidentified. That last possibility brought us back to the light curve. The proposed planet was not found through a clear transit. Astronomers detected weak brightness changes at too low frequencies and interpreted them as light from heated bodies moving through short orbits. The host star's pulsations complicate that interpretation. Different stellar modes can combine to create slow variations that resemble planetary periods. A later study found that the disputed frequencies changed more than simulated stable planetary signals. It also identified combinations of weaker stellar pulsations capable of producing them. The system therefore remains uncertain. NASA currently lists KOI-55b as a confirmed terrestrial planet, while also marking it as controversial. That is where the evidence stands. There is no need to improve the answer by making it more definite than the observations permit. A mystery does not become more scientific simply because we give it a confident ending. Sometimes the correct result is a carefully measured uncertainty. KOI-55b may exist. Its orbit is physically possible. Its proposed history is extreme but not automatically forbidden. Planetary and substellar companions are known to survive difficult stages of stellar evolution. The brightness signal may also be entirely stellar. Pulsating hot subdwarfs create complicated frequency spectra, and the later reanalysis gives a specific mechanism capable of explaining the observations. Either outcome leaves us with something worth understanding. A real KOI-55b would show that planetary cores can survive inside red giants and remain in extremely tight orbits around the exposed remnants. It would be evidence that the death of a star does not always erase every nearby world completely. A false KOI-55b would show how easily a complicated star can imitate a planet when the signal is weak. It would encourage better tests and prevent similar mistakes in future searches. Science advances through both discoveries and corrections. Finding a planet expands the catalogue. Discovering that a signal has another source improves the method used to build that catalogue. There is no embarrassment in revising a conclusion when more data become available. Revision is one of the main ways science separates itself from explanations that cannot be questioned. The Kepler mission was successful partly because it measured so much with such precision. It revealed thousands of planets, but it also produced an enormous record of stellar behaviour. That record will continue to be reanalyzed. New methods can examine old observations more carefully. Weak pulsations can be identified. Instrumental patterns can be modelled. Signals that once seemed uncertain can become stronger or disappear. KOI-55b may eventually receive a clearer status. Another telescope might detect its phase curve at several wavelengths. Astronomers might identify material escaping at the proposed orbital period. A better model of the star may show that the combination frequency explanation is unavoidable. For now, we do not have that final measurement. The possible planet remains useful precisely because it resists a simple conclusion. It asks us to distinguish a physical world from a signal, and a signal from the process that produced it. That distinction applies to almost everything known about distant space. Astronomers cannot handle most of the objects they study. They receive light, particles, and gravitational effects, then reconstruct the sources. A planet may be represented by a dip in brightness. A black hole may be represented by the motion of nearby stars or radiation from heated gas. The early universe appears through old light stretched into microwave wavelengths. The reconstruction works because physical laws connect observations with causes. It also requires caution, because more than one cause can sometimes produce a similar measurement. KOI-55b provides a particularly clear example. A repeating brightness variation can come from a planet's changing phase, or from interference among stellar pulsations. The signal does not tell us which explanation to choose. That choice comes from testing stability, wavelength dependence, timing, related frequencies, and independent observations. This may sound less satisfying than a definite planet. It is more accurate, and accuracy is what allows the next observation to be useful. There is no reason to feel disappointed if the planet eventually disappears from the catalogue. The star remains. Its history remains. The physics used to model a possible survivor remains relevant to real planets around other evolved stars. There is also no reason to dismiss the planet before the evidence is settled. Nature has produced many systems once considered unlikely. Hot Jupiters, planets around pulsars, compact multi-planet systems, and worlds orbiting white dwarfs all required astronomers to expand their expectations. The correct position is not disbelief or certainty, it is continued attention. You do not need to continue that attention tonight. The scientists and telescopes can keep the problem. Your role has only been to follow the evidence far enough to understand why the answer remains open. You can now notice the room again. Perhaps the lights are off. Perhaps a screen is casting a small glow. Perhaps the sound of the narration has become less important than it was at the beginning. Consider what time it is where you are now. The answer has probably changed since we first asked. On Earth, that change may be measured in an hour or a little more. On KOI-55b, assuming the planet is real, a significant part of a local year may have passed. The planet could have completed several full circuits during this video. It would have travelled millions of kilometres and returned repeatedly to almost the same place relative to its star. Your own movement has been much smaller. Perhaps you've shifted a pillow, turned to one side, or pulled a blanket slightly higher. Both motions can be described through time, although only one is likely to involve molten rock and an exposed stellar core. The distance between your room and KOI-55 is enormous. At roughly 4,000 light-years, the system cannot affect the temperature outside your window, the position of your alarm, or anything waiting for you tomorrow. That is one advantage of studying dangerous objects in astronomy. They can remain interesting without becoming immediate problems. The star can continue releasing intense ultraviolet radiation. The proposed planet can continue losing material. The two faint frequencies can continue waiting in the Kepler data. Here, the room remains quiet. If you have followed the entire journey, you have moved from a public description of an extremely hot planet to the measurements beneath it. You now know why the title is reasonable within the proposed model and why the model remains disputed. You have seen that the host is not a normal living sun and not yet a completely dead stellar remnant. It is a helium-burning hot subdwarf created after severe mass loss. You have seen why a 6-hour orbit is physically possible around a compact star, even though reaching that orbit requires an unusual history. You have seen why temperatures above the sun's photosphere would turn a rocky surface into a changing mixture of melt, vapour, and plasma. You have also seen how a Fourier spectrum can turn tiny changes in brightness into a planetary claim, and how the same spectrum can later weaken that claim. None of these ideas requires memorization. It is enough to have travelled through them. The details will continue to exist whether or not you remember the exact orbital distance tomorrow. The planet, if present, will not object if you forget its estimated radius. The host star has managed without human attention for a very long time. If this journey has been soothing, you can give the video a like and subscribe to Science for Sleep. It helps this quiet space reach other listeners who enjoy ending the day with astronomy, physics, and questions that do not need immediate answers. You can also leave a comment with where you are listening from and what time it is there. It is a simple measurement, but it connects everyone watching from different places. Some listeners may be beginning the night, others may be awake before sunrise, someone may be listening during a late shift, a long journey, or a quiet afternoon when sleep has decided to arrive outside its scheduled hours. The clocks will disagree because of time zones, but every comment will belong to the same Earth. That is a more comfortable planet to share than KOI-55b. Earth has solid ground across most of its surface, water that remains liquid, an atmosphere that does not consist mainly of vaporized minerals, and a year long enough to recover between birthdays. The comparison makes ordinary conditions seem unusually generous. A cool pillow is a small thing until the alternative is a world at 6,800 degrees Celsius. A dark room may feel unremarkable until compared with a hemisphere facing a blue-white star that never sets. Even a slow morning has certain advantages over 4 planetary years passing before lunch. The universe contains conditions so extreme that everyday comfort becomes easier to notice. This does not require us to turn the scientific story into a lesson about how we should live. It is simply a useful comparison available at no additional cost. Your surroundings are here. The distance system is there. Nothing needs to be crossed tonight. KOI-55 will continue pulsing. Some of those pulses come from waves moving through the star. 2 may come from planets, although the evidence has not decided that for us. The possible inner world will remain in the archive with its unusual pair of labels, confirmed and controversial. That contradiction is not entirely comfortable, but it accurately reflects a discovery that has not yet reached a settled end. Astronomy contains many objects in similar positions. Candidates wait for confirmation. Published planets are re-examined. Measurements improve. Names remain attached to signals while their meanings change. The catalogue is not weakened by these revisions. It becomes more useful when uncertainty is recorded openly. Perhaps KOI-55b will one day become a firmly established planetary remnant. Future listeners may hear about the observation that confirmed it. Perhaps it will be removed and remembered as a persuasive stellar imitation. Future listeners may hear how its disputed signal improved the search for planets around pulsating stars. Tonight, it can remain between those possibilities. You do not have to choose one before sleeping. The evidence does not require a personal verdict. You can picture the system in the conditional way we have used throughout. There may be a small glowing body beside the star. Its year may last less than 6 hours. Its outer material may be escaping into space. Behind that picture is the measured star, compact and hot, vibrating in many modes. Behind the star is the Kepler telescope's long sequence of brightness values. Behind those values are the photons that crossed thousands of light years to reach a detector. That chain of measurement is enough. Allow your attention to move away from it now. The orbital period can continue without being counted. The star's frequencies can continue without being separated. The last part of the day does not need further analysis. Let your jaw rest. Allow your hands to remain still. There is no need to check the time again unless you truly need to. It will continue changing without supervision. A distant possible planet can complete its rapid year. Earth can continue its slower orbit. Your room can remain quiet while both motions proceed. Thank you for spending this time with Science for Sleep. Thank you for following the evidence even when it refused to provide a perfect answer. Sleep well wherever you are listening from and whatever time your clock happens to show. For now, KOI-55b can remain where astronomy has left it, possibly circling close to a hot stellar remnant, possibly hidden inside the complicated pulses of the star, and safely far from the place where you're beginning to rest.